Awesome. Still a little bit of record keeping, and that's significant digits. We have to go through the a review of significant digits, and then we can move on to Newton's laws. So let's get to it. Well, I'm going to review the basic rules of SIG-DIG, and then we'll look at uncertainty and talk about how you can determine. So, you know, once you know what significant digits are, then there's certain rules of using them to manipulate, you know, algebraically, and how significant carries through without and under the context of algebraic manipulation, which ultimately points to or is determined by the uncertainty of measurements, which we can then define. But I'm guessing to some degree, again, these things you have obviously been introduced to on some level. So let's just make sure we're all on the same page as we move forward. So, rule one. The leftmost non-zero digit is the most significant number. So examples of that, a couple here. So the numbers 107, 107.0, 00107. So some of these numbers, I'm just kind of exaggerating them in the way that we wouldn't necessarily write them that way, but I'm just doing it so that it emphasizes the point that I'm making the property. Yeah. So I have a series of examples that I've written here in different ways. Same numbers. Well, yeah, same. Well, and they're not all the same number, but same digits, but written various ways. And obviously, this is the simplest rule: the leftmost non-zero significant period, no matter whether you have decimals or non-decimals, is the most significant number in that in these examples. And so let's also do something here. So we'll do something like the most significant number, the least significant number, and the total number of significant digits in the number. So in these examples, the value 1 in all of them is the most significant because it's the leftmost. All right. Yeah. Second rule, in the absence of a decimal, the rightmost non-zero digit is the least significant. So again, the numbers 107, 1070. Well, actually, I guess I could just choose these. Yeah. Same values here. So, well, yeah, I'll just do it again. Yeah, so in these examples, the value 7, so the rightmost non-zero digit is the least significant. So in this case, obviously that 7 is that value. In this case, there is another digit beyond, the 7, but it is 0. So the rightmost non-zero digit is the least, which means that the 0 is not significant. And again, even though in this number there are digits to the left, they are to the left as opposed to the right. So anyway, all those examples are the case. Yeah. I guess I have to write this thing over and over again if I do that. So yeah, again, in these numbers then, yeah, I don't know any other way to do this as opposed to writing it over and over again, please. And total. So here we have the value 1 is the most significant, and 7 is the least significant in all of these. Yeah. Yeah, I guess what happens with that. All right, third rule. When a decimal is present, the rightmost digit is the least significant. Okay. So here are some examples of that. 107 and 0, 107.03, 107.01. And even though this is technically something that could be written, it's not something that you would normally see, but again, just for the purpose of illustration. So most, least, and total. Guess we can start to do that now. So in this particular rule, well, so a decimal is present in all of these numbers, and the rightmost digit is the least significant. So in this case, the 0 is significant. So you can compare 107.0 as compared to 107.0. Since the decimal is present now, then it is the 0, the rightmost digit, that's the least significant. In this number, the 3 is the least significant, the 1 here, and in this case, yeah, so I guess it would be this as well, that 0. So the least significant, the value then is going to be, just to complete this through, is 0, 3, 1, and 0. Now, this rule doesn't incorporate any, just whether it's a decimal or not, it doesn't matter. It's just period. The left, that's the easiest rule. It doesn't matter what it is. The leftmost digit is the most significant. So if you were to compare that to these numbers, in this case, the 1 is the most still, this guy. So then the total number of significant digits now can be determined by these combination of these 3 rules. So In this case, I've got a total of 4 significant digits. This case, a total of 5. Again, 5. And here also 5, between the most and the least. Again, here the most significant digit, as we said, is the 1. So then the total number here, we can now also determine. And in most of these, all of these are going to be 3. So 3 total significant digits between the most and the least, 3 here. And again, most significant non-zero digit to the left, that's the rule. So again, the total number of significant digits here is 3. And now also this guy we can do as well. All right, everything. So the least. Now, I guess I kind of mixed the numbers here. So least here, in this case, this is the least, because there's a decimal there. Decimal here, well, it doesn't matter, but here, so least, because that's a non-zero digit. So the total number, and least, if we complete this chart, we got 7, 0, 7, and 7. And the total number here then, between the most and the least, 3, 3, 4, because of the decimal, and then 3. And the final rule, well, that's what I just was showing you here, is that every number between the most significant and the least significant is also significant inclusive. All right. Any questions about that? Any surprises? All right. Let's make a few calculations to illustrate how significance carries through. Oh, right. Sorry. Before that, let's determine how to just review how to determine significance in the first place, like when you're making a measurement, that is. From using a device like a meter stick or whatever. So when you're making a measurement, let's use a meter stick as a basic example. There's a general rule that something called the least count determines how significant you can make, how significant of a measurement you can make with a particular device. The rule of thumb that I use is that you can always determine a measurement to one digit beyond the significance of the least count. The least count is the smallest unit of measure on the device. So on a meter stick, the least count is the millimeter position or the tenths of a centimeter position. Right? It's the smallest increment of measurement. So let's take a look at that. Least count, kind of an old school term, but I don't see it used much anymore, but it's how I was taught, and I like it. So the least count, the smallest unit of measure on any measuring device. So that's when you're pick up a measuring device, that's the first thing to determine. The smallest increment of measurement. On the device. All right. One can always determine one significant digit beyond that of the least count for a device. Generally. Generally, a measurement can be made to one significant digit, abbreviating here on SIGDIG, beyond that of the least count. This digit is the estimated value of the measurement. And essentially determines the uncertainty. Okay. Okay, let's look at a quick example, illustration, I guess I should say. There's any of those will do. Sorry, talking to myself. Yeah, so let's just take an example of a meter stick. And maybe it looks something like this. Yeah, so just like if I have something like this, uh, hopefully you can see that pretty well. So this is 10 and 11. And then I have a block that's doing something like, let me blow it up, make it a little bit bigger. So let's say that this is a block of wood and I'm making a measurement. And so we just cut off the other ends over here. All right, so again, these represent centimeters. This is a millimeter, right? And let's make this measurement in centimeters. So obviously, the block is at least 10 centimeters and 4 millimeters. So that's going to be 10.4, right? But here, as I said, the least count is the 10th of a centimeter's position, the millimeter, which means by the rules I've stated here, we can actually go one digit beyond that, and it's the estimated value. So again, my eyes can't really see that well without aid, without using a cell phone or something to blow it up. It used to be, but most people, when I was young, I could pretty much tell whether or not an object fell right on any of the hash marks or if it were in between. I'll give an example of in between in a minute. Now, right now, it doesn't look like it's in between. So I would then estimate that the measurement is exactly 10.4. And so the estimated digit would just be a 0. But because I can go one digit beyond that, I need to put that, because based on the rules that I just erased from the 4 rules of significant digits, that because I can place a decimal there, because I can obviously see that it's 10.4 and I should place a decimal there. then if I don't put that, it implies that the number is only significant to 3 significant digits, and that's not true. When I put that estimated value, now because the decimal is there, it makes this number more significant. This value here becomes the determines ultimately the uncertainty to what degree of significance you can make a measurement with this device. So therefore, for any device, the least count actually determines, that's what I mean, it determines how significant the digit is and also tells you what value in that for that device is the uncertain value. So yeah, so this digit would be significant to 4 digits. It would have 4, the total number of significant digits in this case would be 4 because you're placing the 0. And the most insignificant value is going to be 0, which determines the uncertainty of this, this. And I know I haven't really defined uncertainty. You probably have an idea or maybe even know what it is. But, like if I had a vernier caliper or a micrometer, I could make a measurement of this object to more significant digits and, based on these same rules that I've determined. So the uncertainty really kind of tells you how significant you can make, how precise a measurement you can make with the device, because it establishes by applying these rules to a device, it establishes the uncertainty of the measurement. Okay, so that's the case of of a situation like that. Now, if I had another piece of wood that say was larger and actually went to someplace like here, let's say, right, then in this case, now I might not be able to determine. So it looks like this second measurement, I'll put them in purple and blue so we can distinguish between the two. So 10.40 for the purple piece of wood. For the blue piece of wood, it's going to be 1, 2, 3, 4, 5, 6, 7, 8. So 10.8. Now again, the least count is the 8, is in the tenths of a centimeter's position, which in this case is 8/10 of a centimeter, 8 millimeters. And I might not be able to determine exactly where it lies in between the 10.8 and 10.9 digits, but I know it's not on exactly 10.8 or 10.9. And so there you just estimate. And in general, there's a couple of different things that people do. I just say, I just guess 0.5 or 0.05 for the estimated value. If it's not in between, doesn't matter, because you can't really determine, because, like I said, you can't, that would be the next digit, the thousandths of a centimeter's position. And because of the rules that I gave you, you really can't determine what that is with this device. So if it doesn't fall on a millimeter position, I just guess that any guess you make is going to, at that hundredths of a centimeter's position, is going to be just as inaccurate as any other number. So I just say 5. That's what I do. All right. So in that case, still the total number of significant digits is 4, with 1 being the most significant and 5/10 of a centimeter being the least significant. Let's put the units on there. So you can apply those rules to any instrument, a scale, measuring scale. I mean, if it's not digital, a lot of times now all the devices are digital. sometimes even the vernier calipers and the micrometers have little digital readouts on them. So they just, whatever the number is, they've already taken that into consideration and calculated it for you. Generally in a face-to-face class, you know, the first lab that I would do is a measurement lab. And so we, you know, I go through up, you know, these rules, but also apply this to a vernier and a micrometer. Just in the interest of time, and because a lot of times you have digital values, I'm not going to do that right now. I'm going to move on. But now that you know the rules, you could look these up anywhere, like on the YouTube or whatever, and they should go through, and you can apply and generally see that the rules that I've given you here are the basic rules that they're going to use and apply to a vernier or a micrometer, and give you the same, and be able to determine give you examples of being able to measure objects with those. I'm going to move on from here and just do one more thing before we go back on to Newton's laws, just because of interest of time, because it takes a little bit of time to go through and give those examples on that. But I hope that's helpful for you, and I hope that maybe refreshes your memory in case you haven't. For those of you who weren't that specific, and maybe there was something here that you didn't know, that hopefully that was worthwhile to go through that. But the last thing there is to take all of this now, and so now you understand how to determine significance. You've made measurements, right? But now you've got to make calculations. And this is, you know, I know a lot of you have been probably applying the rules that you know to the WileyPlus, and this is the issue that we've been having, right? That doesn't matter what you do, it's going to get marked wrong. So again, just to say a word about that, you know, do your best, do the thing. Don't waste time trying to get over numbers over and over again. Just because most of you who we've taken have talked to me about that, we looked at specifically when we go in. And from my point of view, when I pull up the number, I can show you, we can see the answer. So, you know, I share my screen with you, and sure enough, it's the answer that you had. Sometimes they round it back, right, to something, but you had the answer. So just the protocol that I've been doing for the past couple semesters is just do the homework, turn it in, you know, submit it, get it graded. If you think there's a certain number of problems that have been marked too harshly, just send me an email with the numbers written so I don't have to guess. And then I just go back through and check it off and give you, you know, the majority of the credit back. Let's just do that. Emily, yes.
Hi, Professor. Good morning. I had a quick
Good morning.
question. Correct me if I'm wrong, but for the first measurement in blue, I think, would it be 10.60 rather than 10.40?
Oh, yeah, sorry.
Oh, okay.
Dyslexic moment. Yeah, sorry about that.
No, it's okay.
Wow. Yeah, 1, 2, 3, 4, 5, 6. Yeah, so sorry. Yeah, thank you for pointing that out. Awesome. 1, 2, 3, 4, 5, 6, 7. Yeah.
And so in that case, 0 is still an estimate, right? Like since it's so close to the actual millimeter line.
Yeah, yeah, yeah. I just the mistake is I just somehow saw 4 instead of 6, but the rules are all the same, still the same measurement. It's right on it. You can't really. It looks like it's falling on that position, so the estimated value would be 0 for that particular measurement. So absolutely, yes. Sorry about that. So anything else? Is that good? Yeah. All right. Last thing, let's throw it in here with operations. And also say a word about uncertainty. Maybe have a definition for it. And again, you know these, I'm sure, but let's just, you know, make sure we're on the same page. Operation and significant. Oh yes, let's do it this way. So for addition and subtraction, so I'm sorry, multiplication and division, The rule is determine, you determine the, yeah, that's, so for multiplication and division, let's say we can then, so determine, the significance is determined by the number with the fewest significant digits. So, for example, if I'm multiplying the numbers 5.21 times 0.032, I'm going to 5.21. So based on the rules we just determined, this guy has 3 significant digits. This guy has 2 significant digits, right? So it doesn't make sense that whenever I make a calculation, multiply these numbers, that is, that the answer is going to be more significant than the least significant number, right? That just doesn't make logical sense. So therefore, when you're multiplying and dividing, the least significant digit or value determines how significant that resulting operation, the result of that operation will be. So in this case, you're going to get something like 0. On your calculator, 0.166 and whatever else, so on and so forth. But you know that it can only be significant to 2 significant digits. So then you apply the rules of significant digits again, and you realize that this number can only be significant to this value here, right? So then you you truncate the number to that value, and then use the, what I'm sure you know is the basic rules for rounding off a number. So if I'm going to truncate and bring this back to the, I guess, thousandths of a whatever, the thousandths place, then I have to use the rules for rounding. And the general rules is what you've already been doing, I'm sure, is that since I'm truncating this number to the thousandths place, I look 1 digit beyond that. If that number is 5 or greater, then I round this number up to the next digit in the thousandths place. And if it were less than 5, then when I truncate to the thousandths, I just leave it as is. So in this case, I would report the final answer to be 0.017. Okay. Now, generally, we don't write numbers like this. We use something called scientific notation. Just because when you look at a number like this, you might have to think a little bit, right? Just even a slight amount of time, a slight, number of milliseconds. I don't know how we're, like, because it's just kind of cumbersome. You have, for me anyway, I have to think a little bit about the rules that I just mentioned. So scientific notation is a way of basically writing a number so that you kind of have to think less in terms of the significance. And the rule is that you have an argument, and the argument is the value that you're multiplying the base 10 by. So the way that I would write that is 1.7, and of course, when the decimal moves to the left, that the exponent on the base 10 because the net is what is it, negative? Yeah. So then that's 1.7 times 10 to the negative 2. So this portion right here in parentheses is called the argument. Any in general, any number in a parentheses of a function is an argument, like cosine, or whatever the thing in the parentheses is the argument. And same thing for like log functions, whatever. But technically speaking, the argument is written to the number of significant digits that you should have. So like, yeah. So like this is not a good example, but if I had like, whatever, I just leave it at that, right? So you can see just on first glance, when I look at this, just the two significant digits clearly jumps out at me. It's almost I don't have to think, at least but when I look at something like this, I might have to think just a little bit just to make sure. And so if you have a bunch of numbers like that, written, obviously it's going to be easier to use scientific notation because it's just much more clear at first glance that the value of the significance of those numbers, and it kind of reinforces it, right? Like if you've taken the time to convert a number to scientific notation, then it just gives confidence that somebody, if it's done correctly, has thought about and specifically enforced the fact that this is the significance of whatever that number is representing. All right, and then finally, addition and subtraction. Oh, and by the way, again, going back to the WileyPlus, I think I said this the other day, but WileyPlus does not take this a number written this way in terms of scientific notation. It will always mark it wrong. So what you have to write is this number in scientific notation for WileyPlus would look something like this: 1.7. You still go through technically, you should go through all the the argument should still be written to the correct number of significant digits, but then without any spaces, you write a capital E and then the exponent, in this case, -2, without any spacing whatsoever. Now, again, because of the rounding off, sometimes it still gives you issues with that taking off, something. But if you don't write it like this, even if it's right, it won't give you any credit whatsoever. Like if you write this, it won't even give you partial credit. It'll mark the whole thing wrong. So this is how you have to write scientific notation for WileyPlus. Okay. And finally, then, addition and subtraction. The significance is determined by, what I have written here is the number with the least uncertainty, i.e. the fewest digits to the right of the decimal point. So I guess I said that a little bit different just to emphasize the idea of uncertainty. I could have used that terminology here as well, right? And again, it's the same logic that if you think about it, that is essentially what is being determined here with these operations, with the, like I said that based on the rules that we had, this guy has 3 significant digits, this has, 2 significant and 3 significant. So if this were a measurement, for example, from a meter stick, then, well, I guess we won't say that because we don't, it would have to be like a more precise value. I don't know. Yeah, we don't know where the numbers come from. I won't say that, but yeah, whatever. Let's just, I'm gonna move on to this example. So determined by the number with the least uncertainty. And I guess I'm determining uncertainty by the number of digits. Yeah, the fewest number of digits to the right of the decimal. And sometimes it doesn't have a decimal, but still in the case, I guess the fewest number of digits. Yeah, I don't know. I guess we're gonna, yeah. I've never known any way to say this comprehensively. What language to use? I don't know. I've never been able to figure it out. So, because sometimes obviously you can write numbers without a decimal, and in that case, I guess you would say it's the numbers that I don't know what language to use. It's just easier to give examples. But generally, because we do have decimals when we write the values, at least I can, if the values do have decimals, then you can say this. But once I give the illustration with decimals, I think you'll see what I mean, how you can apply it to a number that's not written with decimals. Anyway, fewest number of digits to the right. Decimal. Oh, I guess I just thought about it. If there is no decimals, then it's going to be the number with the fewest non-zero digits. Yeah. If there is no decimal, then it's the number with the fewest non-zero digits, period. Yeah, I think that works. So fewest number of digits to the right of the decimal, or let's write this like this. So these are points, subpoints above below this. Fewest number of decimals to the right, or in case of no decimals, it is the, what did I say? The value with the fewest non-zero digits. So that would be how you would practically determine the 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 number with the highest uncertainty. If there are decimal points, it's the number with the fewest decimal. Sorry, if there are decimal points, it's the number with the fewest number of digits to the right of the decimal. If none of the numbers have decimal points, then it's the number with the fewest non-zero digits. It's going to be the least certain, or yeah. And I think I have a double negative here. It's determined by the number with the least certain amount, or the highest uncertainty. Right? I don't know why this always just trips me up. I think it's just hitting my whatever. Determined by the number with the yeah. I said yeah, that was a typo. I said least, but it's actually largest. Yes, sorry, because there's a it's the uncertainty is a word that's written in the negative, so it's like having a double negative means the opposite of the thing that it implies. So my bad. So it should be largest uncertainty or highest uncertainty. Yeah, the highest uncertainty. All right. So yeah. And if you're writing, so basically you probably already know how to do this, but I just want to make sure in terms of the definition of certainty or uncertainty, you know what it is and why you're doing it. So 35, if you add a number, 35.213, and you're adding that to, I don't know, so subtracting, let's say minus 29.1. So you're going to get something like, yeah. So on a calculator, would that be like 6.113 or something? Let's see. Make sure. Yeah, 6.113. Or sorry, 6.113. So again, it's the same. This would be kind of contradict logic, right? Clearly, this number is the largest uncertainty. So this number is more certain than this number, because if I'm making a measurement and all the numbers are significant, I've taken this number out to the thousands, to the thousands of a decimal place. And this number, 29.1, is only correct or certain to the tenths of a decimal place. So this guy is a more accurate or more significant and more certain value in terms of measurement than this guy. So it doesn't make sense that if I'm making manipulation and calculating numbers, it doesn't make sense that the result should be more significant than a number that was had a smaller significant, or should be more certain, I'll use that term, because more certain than a value that I use to calculate that number. So that's how this number that is more uncertain is determining the certainty of the resulting value. And so in this case, it's determined by not the total number of significance, because this has 3 significant digits, but it's determined by the most, or the least certain value, which in this case is in the 10th place for 29.1. So that's why when you're adding numbers, the resulting number can only be significant to, or certain to the 10th place. And therefore that would dictate the number of significant digits in that value. So, and the rule then when you're adding and subtracting is just whatever the least certain number is, that becomes the, you truncate all the numbers, in this case, to the right of that value, whether it's a decimal or not. And so, and of course, you still, actually, there is no rounding, right? Because, right, there's no rounding when you are, or yeah, it's the estimated value. So you do round. So you truncate and you round there. In this case, since it was below 5, the number in the 10th place, then below the value 5, when I truncate, then I just leave the number in the 10th place, in this case 1, as it is. And so this is the value that I would report as the final answer for this operation. And then the resulting answer would only have 2 significant digits, the number in the 10th place being the most, being the estimated value and determining the certainty of that final result. And finally, after saying all that, for orders of operation, I've been saying this quite a bit when we've been doing our calculations. When you're rounding a number, you don't do it to the very end, right? So let's say that I had a bunch, whatever numbers, and I'm doing calculations. If I now use this number here, and then and really it's kind of more implied for multiplication and division, but anything, it doesn't matter. If I round off every time that I get a result, then in the end, I'm introducing round off error into my final result. So the thing is that you want to get accustomed to storing all values in your stored registers as you make calculations. And then when you're reporting the final answer to the correct number of significant digits, you reduce the amount of round off error that can be truncated in, that can be translated through your operation, your mathematical operations and calculations. Oh, okay. Record keeping is over. Let's get back to physics. Well, I hope you didn't find that a waste of time. I'm sure most of what I have said here, you probably already knew, but there might have been 1 or 2 things here or there that you didn't, or that you just needed to be reinforced so that it's not challenging your confidence. And again, this is an introductory course here, this of all the 3. So of all the courses, this is the place where those little details should at least be addressed. And so even though it takes time, and I just feel like over the years, for several reasons, it's just my experience to go ahead and do it, and at least once. All right. Any questions, problems, troubles, and or gripes? And also, I promised you that I would be comprehensive, so as comprehensive as possible. So I'd like to honor my word. I need to take a quick break, 2 minutes. I know we're not at 9:30 yet, but I need to take about 5. Um, what we're going to do next is introduce Newton's laws, Newton's laws of motion. And again, many of you probably know various versions of these. When I come back, I'm just gonna, maybe just have a little dedication, if you will, homage to Newton. I like to do that because it's just so significant and the foundation of basically the modern era. So you might maybe take a note too. I don't. Sometimes I put these little exposés in the module. I don't think I did that for this. They're here, but just take a minute to either Google the laws. If you don't know them, you probably do. Just review them real quick while I'm doing the break, and then um, we'll come back and we'll say a word or two about them, and then we'll go into the laws and start to introduce them, and all 3 laws, kind of as a quick review overview, and then we'll go into each of the individual visual laws and look at them quantitatively. So give me about maybe 7 minutes. Thanks. Okay. So Isaac Newton. Probably certainly the father of modern science, maybe. Most physicists, even Einstein, would say that they stand on the backs of certainly people like Newton, but of all the forefathers, I think Newton probably is, well, for me, he's probably the most influential physicist, all things considered. There's a standout in every generation. Every 100 years, there seems to be like a standout genius. I guess at least in the early part of this century, Hawking, before he passed, probably takes that and probably would be in that category. So for in this millennium, the 24th. So what? No, sorry, the 21st millennium, 21st century. But we're kind of early in, so we'll see about that. But certainly Hawking probably would be considered the standout physicist. Obviously, it was Einstein. In the 1800s, it's probably someone that you never heard of before, but we'll talk about kind of two of them together. But we'll talk about them in electromagnetism, and that's James Clerk Maxwell, who was quote unquote discovered light, but the father of well, it's kind of two. It's James Clerk Maxwell, who was kind of the mathematician who organized it, basically developed the theory. But it actually, and he probably did this around the time of the Civil War, 1860s, and between 1860 and 1860, right around when the Civil War, 1864 or something, is when he came out with his paper, which is right at the time that the war ended. But it had started in the 1820s, by a guy named Michael Faraday, who was not so formally educated, but was basically a genius and had insight and a lot of insight and defined certain phenomena that because he wasn't formally educated, not everyone took him seriously until this young, brilliant mathematician Maxwell came along, studied his work, then compiled it and was able to put forth a theory. So they're kind of both to stand out, James Clerk Maxwell and Michael Faraday of the 1800s. In the 1700s, then it was Isaac Newton. Isaac Newton lived between 1642 and 1727 and published his Principia, which is masterwork in the early 1700s, I believe. 1600s, probably Galileo. And then going back before Galileo, I think probably Kepler's next in the 1500s. So 14, no, wait a minute. What did I say? Yeah. 17, yeah. And so Galileo, that is, in the 1600s. Did I say Galileo? I don't know. And then, okay, no, 1500s, probably like Kepler. And kind of crosses in. There's Kepler, Copernicus, and yeah, one of the other astronomers around it. I forget his name. Tycho Brahe, I think.
I mean, this crazy. He turned down $1 billion.
Yeah. In fact, if you go up to the observatory, you can see it from my window here. They have a homage to the those, I think those first, basically the people who took us out of the dark ages. So it was the astronomers, I think, starting with Tycho Brahe, and then Copernicus, then Kepler, and then Galileo, and then Newton. I think the four of them are the people that they have on the that monument there at the observatory. And you follow the physicists, it kind of follows the evolution of man in terms of what we have, what conventional science tells us is the kind of the timetable of our awareness. Prior to the 1300s, there wasn't much change. There was the Dark Ages, which probably went from the 1100s, to the 1300s or so. Before that, there was a couple, 200-300 years there where there was chaos all over the world, which led to the Dark Ages because of the fall of the Roman Empire. So the Roman Empire, I think, probably fell around the 700s-ish, 600 to 800. So I don't know the dates. And they were in control from, before the birth of Christ, it was like 600 years or so, 600-700 years. And you got to go back to the beginning of that, when they came, like, I think so, there's like a 600-700 year period where, prior to that, I mean, there really wasn't much growth that we know of in terms of recording history from the Greeks, right? Take something like light. I think it was Plato or maybe Aristotle, whoever was the teacher, I can't remember, came up with the idea that light traveled on ether. And that was maintained up until the time of basically, the astronomers in the 1300s. So you're talking about 1,000 years where knowledge, and again, this is recorded history as far as I know, didn't really grow. So when you put that in context, and prior to that, who knows? I think that I won't get into that soapbox of mine, but we are taught that our evolution started probably about 5,000 years ago. But there's all, I think I mentioned there's all kind of evidence that maybe life isn't really linear like that. Like we came out of the caves, and the Sumerians were the first civilized society, and the Babylonians, and they introduced math and numbers and the concept of zero, and presumably, that was 6, 7, 5, a little sometime before 5,000 or 6,000 years, and from that point on, our insight has grown linearly, and we're the top of the food chain, so to speak. But you look at the age of the Earth, and that's not the only model that fits. I think that you could think of a cyclical model because everything else is cyclical in terms of energy and down to what quantum mechanics is predicting. I think I mentioned something like that. At any rate, it puts in context what Isaac Newton did. Because everything that we've done since then has literally been built on what this man gave. What did he give? You can summarize it in 3 basic things. 2 of them are physics, and some of you may not know, one of them is so basically he gave us 3 things. The laws of motion, which we're about to study, the concept of universal gravity. I mean, he gave other things, but these are the main things that he's known for. There are other things that he actually did. I won't get into it, but I'll give a little reference here that you can take a look at that if you have time at some point, which is a really nice, interesting program that kind of gives a synopsis of Newton. But at any rate, the laws of motion, which we're about to study specifically now, the universal law of gravity, which we'll do a little bit later in the semester, and that's what was published in the Principium. But what you might not know is that, and I mentioned this earlier at the beginning of the semester, is that Isaac Newton invented differential calculus. And he had to do that in order to prove basically the laws of motion and the universal gravity to be able to prove it theoretically. And clearly, math and physics, I mean, think about that. Everything everything from finance, and the stock market and being able to predict and calculate the flow and change of financial markets to, the weather, to, I mean, everything, all of this stuff, everything, building buildings and being able um, to predict the outcome of architecture and construction with minimal loss of life and catastrophe. All of that is built on on Isaac Newton, what he gave, all of it. And think about what I mean. Like, I'm not trying to say that people weren't brilliant before that. They were, right? You look at the Romans and the aqueducts and the pyramids, but what you might not have thought about is that those things came at a huge cost of life and freedom based on our sensibility today, right? Those civilizations had slaves, and they learned things by trial. There was no theory, right? So they learned things by trial and error, meaning we go look at something like the Parthenon now. Did my honeymoon last summer, the Parthenon, and went there, and it was just beautiful. The thing is like, over 2,000 years old, and it's a magnificent, like, in these places even older than that. You go to some civilizations like the Incas and stuff, and you go to like Machu Picchu and stuff, and you know, and there's these bricks and put together and with such precision, and there's no mortar or anything like that. That's why I think that really civilization wasn't linear. I think we lost a lot of knowledge that probably certainly rivals what we know now. But still, the point is that as far as we know, in terms of recorded history, the way that had to be done is that they built these things, they fell down, they recorded the mistakes, and just by trial and error, they kept building things until they didn't fall down. So what we see is the final result of that. But because they had slave labor and their societies were constructed different, you just put slaves out there and things fall down, kills a bunch of people. Oh, well, maybe that's not the way to do it. So we'll do it this way this time. And you just keep doing that until, the thing works. I mean, I don't see any other way they could have done it unless they did have calculus back then and we just don't know that, which again, I'm not throwing out that possibility like conventional history does. But that said, here we are. Certainly by the time we got into the modern, age, like the past several hundred years, that was also, the only way we would progress is by doing that, progressing that way again unless someone like Newton comes along and introduces. And even with that, obviously, there was still a lot of practice that, life was very harsh. And that's what. So the point is that this is what this man did. And the contributions, physics is a foundation of all science. So, and certainly calculus. So it can't be underestimated, I think, the significance of the contribution of Isaac Newton. And I think it's worth mentioning to kind of put it in perspective, especially given all the presumed problems that are on the horizon that we'll have to solve, and whatever new science we come up with, that we'll have to come up with in order to survive. I think it's very important to definitely look back at the past. There's that famous saying that if you don't know where you come from, you don't know where you won't really know where you're going, or you'll get lost. So I think I always like to give a little bit of a shout out to and a nod to those who have come before us. And of those who come before us, Isaac Newton was kind of a badass. So that said, you might take a look at the current standout physicist, Neil deGrasse Tyson, was involved with the remake of a show called Cosmos, which was first introduced by Carl Sagan in the 70s, and they kind of did a remake of it. There's been 2 seasons. Season 1 has a couple of shows that I think episode 3 and definitely episode 3 gives kind of a synopsis. And nice thing about Cosmos, you can find it on a lot of the streaming platforms, is that they have like little cartoons where they illustrate the history, and it was really well done. It's actually, I watched the one in the 70s with Carl Sagan. We would watch it in science class in elementary school, or certain episodes, and it was really good at the time, to kind of open your mind. But I have to say that the remake was just as good or better with Neil deGrasse Tyson. But there's one in particular called When Science Conquers Fear. I think it's episode 3 of season 1. So season 1, episode 3 of Cosmos with Neil deGrasse Tyson. If you can look it up, it's probably our program, I think. It would be a nice one to watch to give you a little bit more background and the sensibility of Isaac Newton based on his upbringing and issues that he had as a child. And it shaped his kind of perspective about, and talks a little bit about, and you might even look up a few things about how he lived, and things, maybe dig a little deeply, because one last thing I'll say, and then we'll get to we'll take a break, and then we'll get to the physics, come back and get to the physics, is that sometimes in my little soapbox, I kind of get into a little bit of what a lot of people would call, or at least point to it, what a lot of people would call pseudoscience, or metaphysics. Well, metaphysics is not, that's not really something that's, alchemy, and, you can look up some of these terms. And again, I have to be kind of conventional and teach what's taught, but I also feel obligated to inform you about just make you aware of the limits or the borders of what we consider to be conventional or accepted science and other things. And the reason I think that's important, obviously, is because of stories like Galileo, right? Galileo was considered a pseudoscientist and was thrown in jail because he said the Earth was not the center of the universe. So at the time, considering astronomy and certain implications was considered by the powers that be pseudoscience. Well, clearly, we don't have to go on that soapbox again. You can see the problem with that, right? It's pseudoscience until it's not. And who determines that? The scientists, who are not always in control. So that said, there's a lot about Isaac Newton that has been suppressed, and it is true, it's real. He was a straight up alchemist. And I'm talking about in the sense of what we think of mythology, like Merlin and those things. Like, he did things like, for his entire, he was a devout Christian, and he scoured the Bible for patterns, and those movies like the Da Vinci Code and all those movies. Da Vinci, Isaac Newton, all these, and all the kind of conspiracy theory in those movies, all that is based on truth. These guys were alchemists, Galileo, Isaac Newton, and they were in these secret societies. All that's true. It's true. But it's kind of been suppressed because it's not kind of what we consider to be conventional for a lot of reasons. I don't know. There's a whole bunch of conspiracy theories about that. But Isaac Newton was straight up. He was literally a dude who believed and searched his whole life trying to, you know, turn base metals into gold and all the implications associated with that. If you read all of that, if you have read anything about that, that was a literal thing, but it was also kind of an allegory for transmutation of reality. Yeah, on that level. And that dude was straight up into all of that. But he also was embraced by the queen, and he was very practical because a lot of the things he did, obviously, as I've been saying you, had practical implications that clearly bettered society. So he was one of these people, unlike Galileo, who was incorporated and embraced and controlled by the powers that be at the time. But if you have time, it's worth it to maybe delve a little deeper because you have information now with the internet. We're in an information age, so you can find that information. So that said, I'll just leave that, let that be there. But this program is very conventional and it gives a really nice kind of expose of Isaac Newton in the context of talking about some other science. And the name of that show is I think it's something like When Science Conquered Fear or something like that. And they don't really get into the metaphysics stuff in this, but it's still really good, nice introduction. When Science Conquered Fear. All right, so let's break right now. Let's take 15. When we come back, we'll review, give a synopsis of Newton's 3 laws of motion, and we'll go on from there. All right. Thank you. Could you? Sorry, something must have been wrong. So can you hear me now? Anyone? Is anyone there? Testing,
We can hear
testing. Is
you.
anyone there?
Yes, sir.
Awesome. Luz, how? Good. Thank you. Yeah. So the laws of motion. Can anyone give me can rattle off the laws of motion, just the names of them? Luz, what about you? Do you know any of the laws? Names?
Laws of motion. Oh my gosh, I learned this like a while back ago, and I always confuse it with like laws of like Newton's laws of gravity. I always confuse it with that. Yeah.
Okay. No worries. um, okay. What about you, Antonio? Do you remember any of the laws? The names of them?
I looked them up a while ago. The first one's about inertia, which we did the discussion on. The second one's kind of like about force, and
Yes.
the third one is about normal force.
Yeah. Reaction force, action and reaction, we
force.
say. Yeah, and the normal force is often the example that's used. Action and reaction. Awesome. I have pet names for them. My pet names are inertia, which is actually the name, cause, which is kind of a poetic name for force, and karma, because karma is kind of generally a word that kind of implies a universal reaction to some action. So yeah, action, reaction. Yeah. And they are in that order, right? And that might be also something that Luz was implying. So the law of inertia, the force law, and the law of action and reaction, inertia cause karma. That might help you to keep them in order and give you kind of a little, well, it's not really a moniker, but some sort of jingle maybe, or rhythmical phrase or rhythmical way of stating that can help you remember. So let's go through and describe them. Now I'll do that, kind of move it along. The law of inertia. Well, we can talk a little bit more about the relationship between inertia and what that is, but the law of inertia states that an object will stay at rest an object will remain at rest, an object remain at rest or in uniform motion in a straight line. Unless acted upon by a net external force. And the external force is usually represented by a summation sign with force. External meaning a force that is external from the object itself. All objects can have internal forces, molecular forces, that sort of thing, but those forces can't cause an object to move or accelerate unless it's already doing so. Well, whether it's doing so or not, it's not caused by those internal forces. has to be some force external to that object. So that's it. That's the law of inertia. Now, generally speaking, I like to write an equation and associate, like associate equation with a concept, whether those equations describe the parameters or the, the criteria of that, applying that concept or describe the concept. In this case, you don't normally see one in most books for the first law, but I like to establish one again for purposes of the problem solving technique. So what we will show is that if there is no net force on an object, then the object will not change its motion. The basis of the first law is change in motion. It's kind of like written in the negative, which it's a little bit more to it than is obvious because of that, because it's written from the negative point of view. If there is no net force, then basically nothing, again, a negative, is going to happen, or nothing is going to change. So you have to kind of view it in that context. So we imply no net force with this equation. The net force, external force on the object is equal to 0. So I use that as a basis, as an equation that actually is an illustration of this law. Now, a lot of people might criticize that and say, well, it's just the second law with no acceleration. Well, it is, and that there is a connection between the first law and the second law. So if there is no, and with the first two laws, I like to kind of break the laws, because we usually write them like this with force on the left and something about motion on the right. So I like to distinguish between the motion side and the force side, that is the kinematic side and the dynamic side of the first and the second law. Third law, not so much, but the first and the second law, yeah. Kinematic side and dynamic side. So we're saying here, it's not that we're saying there is no motion. The right side is really about change in motion. So there's no change in motion if the net force, there's no change in motion if there's no net force on the object. Now, there can be forces, they just have to sum to 0. Like right now, are there forces on me right now? Yeah, there are two. There's the normal force, as someone mentioned that, I think Antonio, and it's basically a reaction of the floor on me. And we'll get to that on the third law. And and I'm pressing on the floor. Well, but again, that's not a floor. Sorry, let's back up. Actually, good point. We're going to do an illustration. The force that I'm pressing on the floor is not on me, it's on the floor. So that's not the other force that's on me. The two forces that are on me are the force of gravity due to the earth that's pulling me down. And because it pulls me and puts me in contact with the floor is keeping me from going down further and pressing back on me in the opposite direction. So the two forces on me are my weight, the force of gravity on me, and the normal force, which is the force of the floor pressing on me. But clearly those forces are summed to 0. How do you know that? Because my motion is not changing, right? So that means that whatever those forces are, they must have the same value. My weight that's pointing down must be equal to the normal force pointing up. And when you add them all together, remember superposition, I told you it really applies. We usually apply it to force more so than kinematics, like we were doing the past couple of days. But when you superpose those forces, add them all up, considering their vector direction, they sum to 0. And I can clearly illustrate that here, right? I can say, okay, this is a surface. If I have some mass sitting on a surface, that object has two forces on it. One is weight, acting straight down. Weight is defined as mass times the acceleration due to gravity. We defined that already the first week. But there's another force of the ground pressing on the object, and just by looking at the object and seeing that it's not moving qualitatively, even without measuring quantitatively, I can say that those two forces must be equal, right? Because when I superpose them, the left side of this equation, they're clearly in opposite directions. Vectors, you represent the opposite direction of vectors with by a sign, with minus sign. So the normal force minus the weight, that's the summing. It's got to be equal to what? Well, there's no motion, it's not changing. What we'll show is that, that is the acceleration, the change in the motion of the object. So that must be zero because it's not moving. We have to analyze the motion first. With Newton's first and second law, you always have to analyze the motion of the object, not only to execute and apply the laws, but even to know which law to apply, whether it's the first law or the second law. We'll get into that. Once you analyze it, that is a way to prove quantitatively that those forces must be equal. Because once you establish that the motion is not changing, zero, and you establish that the vector sum of those forces, the superposition, then you have an equation that you can solve for one or the other and show simply that that must mean that the normal force is equal to the weight. So that's a direct application of the first law, and that's the way to apply it, which is why I like to use this as the equation that represents the first law. So an object will remain at rest or in uniform motion in a straight line unless acted upon by a net external force. Now, uniform motion, that remember, I told you this thing is written kind of in the negative. Uniform motion specifically refers to, you can actually translate this, constant velocity. In this equation, remember, specificity is a characteristic of, is a property, a theme that I refer back to a lot, as I mentioned the other day. Motion specifically means velocity in the first law. And so the uniform portion is not referring to acceleration, it's referring to velocity. And he specifies this because we're saying that the motion can't change. And as we know, because velocity is a vector, even though its magnitude doesn't change, if its direction changes, that's also a change. And that has to be brought about by a net external force. So neither the magnitude of the velocity nor the direction of the velocity can change in order for the first law to apply. So Isaac Newton is being very specific, with this law. Uniform motion means, but it also implies a couple of things. It implies that there's a couple of ways that you can have a net force be zero. One is that there's three ways. One is that there's no force on the object, which I guess you'd have, technically that doesn't exist anywhere in the universe, but surely if you're out in the middle of space, very far away from massive objects, you can approximate no net force on an object. So whatever its motion is, which will have motion, it would just be moving on without changing its motion. Right? The other way is what I showed you, when you have forces on the object, but they sum to zero, in this case. And the motion is, there is no motion, it's stationary. But the third is really constant velocity. If you're moving down the highway and you're not accelerating or changing your direction, there are forces on the object, right? Both in the X and Y directions. And clearly those forces must add up in all directions to be zero. So zero motion and constant motion are the two main ways that you can have a net force be zero on the object, other than the obvious trivial case that there are no forces to contend with at all. Okay, that's an introduction of the first law. Let's get into a quick discussion about something I'd like to point out about the first law. Let's give an example to start this illustration before we go to the second law. I like to call this the discussion, a little my kitten. There's a famous experiment in quantum mechanics associated with measurement and kind of an implication of Heisenberg uncertainty principle. The whole Schrodinger, well, basically, the Schrodinger cat example that discusses some implications of the probability nature of quantum mechanics. But I have a little kitten that I like to talk about, Gamble's kitten, Professor Gamble's kitten, which has nothing to do with quantum mechanics, but it's an example I like to use to discuss implications of the law of inertia. I'm sitting on a train track with in my chair, just hanging out with my tea and enjoying the beautiful nature or whatever around me. And it looks like it's a defunct train track, but turns out, as we'll see in a minute, it's not. There's a stray kitten that's walking toward me, playing around on the train track, and sees me and starts to kind of bounce and wobble and come toward me. Now I'm sitting stationary, I'm not moving, and the kitten is walking toward me. It's small kitten, I don't know. I'm much more massive than the kitten. Kitten starts to walk toward me at let's say 1 meter per second. And just to give you a gauge, I don't think we did this with the motion. I did that experiment of walking across. Well, we did, yeah, actually I did do it, yeah. So I walked across the room and dropped some papers, and we measured my velocity to be whatever it was. It's anywhere between 0.5 and 3 meters per second. I think that day it was probably a bit less than 1 meter per second. So that gives you a gauge of what 1 meter per second looks like. You have an intuition now because we literally had a very wonderful basic experiment with pieces of paper that we figured out how to determine how fast someone walks across a room. So just imagine that with your intuition, the kitten is walking toward me at about 1 meter per second. Emily Reyes, when that kitten bumps into me, what happens to me?
Is it just, I'm trying to visualize it, sorry. You would get hit then? You would get bumped into the kitten?
Yeah, it would bump into me. And in terms of my motion, does my motion change when that happens? Why not?
I think it would, the way your position is at, I think.
Emily Bogazian, you want to add on to that? Now, keep in mind, like we're making this practical, like I'm sitting, there's friction, right? And even not inconsistent friction because there's gravel and wood and whatever. And so it's very, like it's not like a smooth surface. And I'm sitting there and the kitten walks into me, bumps into me, and I'm much more massive than the kitten. So does it really affect my motion in any in any reasonable way?
I'd say that because because the force isn't greater, I'd say that your body would more likely prefer to stay in a state of rest. So I'd say that you wouldn't necessarily move. That's what I'm thinking.
Yeah, I mean that's kind of what I'm getting at, Emily Reyes. It's not like it's a very small mass, and certainly, and we haven't defined momentum yet. We'll do that later on with some when we get. Well, I'll actually do it when I get to the second law in a minute, and then we'll come back and talk to it later. But yeah, it's a small cat. Like it is. Don't overthink this, right? It's a very small cat. Cat's probably, I don't know, it probably isn't even a kilogram. Probably less than a kilogram. Just I don't know, maybe a kilogram is 1,000 grams. Yeah, it's probably a kitten, a very small kitten. Yeah, probably. I don't know. At least and I'm like 80 kilograms approximately. So it hits and it's going pretty, 1 meter per second is not very fast at all. It just hits me and I'm not going to move. It grabs me, jumps on me, starts to play, whatever. But like just the actual initial impact, it doesn't really affect my motion. Right. Now I take the cat, I pick him up, put him on, and we start playing around. He's on my lap. Now, a few minutes later, then there is a large train that's coming down the track. Also and it's let's say it's a old style caboose, freight, old style, what do you call those, steam engine type thing. And it's got the cow tipper on the front. You probably didn't know what those are, but when you look at those old movies, and there's this thing kind of like a fan that looks out that is on the front, cow tipper or cow scooper thing, because like dead animals and things, or so cows would sleep on the track or whatever. So you got the train. I don't know. I can't really draw a train, but it's something like that, right? Got the caboose. All right. On those old cowboy movies, there's always something out front that kind of looks like this. The fan that kind of would go around, right? And it's actually very low down, kind of close to the track like this, right? And basically it would scoop like animals or dead things that it or debris or anything that had fallen on the track, so it wouldn't derail the track as the train went into it. So they don't have those anymore because usually there's not stuff on tracks. But back in the day, in the 1800s, they did have that. Now, let's say that there's one of those things on the track, on the train. And the train's only going 1 meter per second, right? So that's pretty slow. So when it hits me, so it's going to hit me and the cat, right? But it's not going to kill us. It's going really slow, right? So it's not going to hurt us or anything. So let's just, make that assumption. And we don't get caught under because we got this the scooper thing there. But obviously the train is much more massive. So Emily Bogazzi, I want you to go with this one. I called you, but didn't give you a chance to speak. When the steam engine runs into me at 1 meter per second, what happens? What is the resulting motion of the collision?
Trying to think. I'm having a little bit difficulty visualizing it.
Why?
I'm not sure. I feel like I don't know. I want to say that, like, you said it had 1 meter per second speed.
Yeah.
Mm,
Do you know what 1 meter per second is? Can you visualize what that looks like?
yeah, it's pretty fast,
Okay.
right?
No. 1 meter per second?
Like for something on the ground.
Yeah. I think we're overthinking all this. When I walked across the room and dropped those papers the first week, and remember we did that? Like when we did the graph on the board, it was about 0.7, 0.8, something like that. That was just this. Like this was how fast I was walking. Right. So something like this is about 1 meter per second or less. Right. That when I assume that we remember that, I dropped the pieces of paper, we graphed it, we did all that, it was when we were defining constant velocity or whatever. And we found that you could use that kind of graphical representation of that data to determine the average value of my speed, which was about, so people, when we're walking, people walk usually a little bit faster than that, but someone briskly walking on a New York sidewalk, they're probably going 2 or 3, maybe twice that fast. So that's only about 2.5, maybe 3 meters per second. So that gives you an intuition about what that speed looks like. And it doesn't matter how big the thing is, if that's the speed, that's the speed. So we're saying that the little kitten was going that fast and ran into me. Because we've established that because the kitten is very small, it doesn't affect my motion, right? It's almost like, I don't know, if I took, yeah, I don't know. I mean, I don't know. I don't want to make it more complex than that. So, but now I'm saying you get something very massive like a freight train or a steam engine, and it's also moving with the same, let's say it a different way. If you see the train moving along at 1 meter per second, and I get up and I put my hands again and try to stop it from moving, will I be able to stop it? Eric Acosta, will I be able to stop that steam engine if it's moving at 1 meter per second? Maybe Eric's not there. What about Meredith? Are you there?
Yeah,
Oh.
Can you repeat the question?
Yeah, Eric says he's here. Yeah, so for both of you, Eric and Meredith, can I stop the freight train, the steam engine, if it's moving at 1 meter per second, and I try to push against it and stop it? Will I be able to stop it?
I want to say no.
Why do you want? Like, why is it a question? Like, why? Is there a disconnect? Like, and you say you believe so. Like, why don't you know for sure?
Well, and I'm assuming that because but the freight train will probably have a different weight than you, you won't be able to stop it. But I might be missing something.
No, be confident. Yeah, I mean, yes, this is, don't overthink this. Like if your car is rolling along, like down a hill or something, and well, let's not do that. I don't know. But like, I don't know, maybe, yeah, like it's a big thing, right? So it's very difficult to stop the thing. Like, even with your car moving a little bit, you might be able to do it a little bit, right? If it's not a big car and if it's not moving along very fast. But, like it's a more massive thing, and mass, not weight, because that's the thing we're talking about. Like, I know we're making a distinction. It's not so much the weight that's the issue. In fact, it's not the weight that's the issue. What we're going to see after this discussion is over is that's really the mass. But yeah, you're on the right track. And yeah, don't overthink it. It's a old school freight engine. It's like, if a car is about a ton, a steam engine, I don't know, probably about 10 or 15 tons or something, like it's a very massive thing. So the point that I'm trying to make is that when that freight train comes along and makes contact with me and the kitten, it basically is not going to stop moving. It scoops us up and we just, or scooped out of the way or whatever. Like, it's almost as if you could look at the change in motion, it's technically speaking, because of the law of conservation of momentum, technically speaking, there has to be some kind of change, but it would be so minimal that if you actually looked visually at the freight train when it or the steam engine when it comes into me, it would look like its motion didn't change at all. Right. So very different results when the kitten bumps into me at 1 meter per second, as opposed to the steam engine at 1 meter per second. So the question is, why is the resulting motion so different for the kitten as compared to the freight train, to the steam engine? Why does the kitten stop, but the steam engine does not when it interacts with me during the collision? And I think Meredith kind of alluded to the fact that, well, they definitely have different weights, but they have different weights basically because they have different mass. Why? Because of the definition of weight. Weight is mass times acceleration due to gravity. But the acceleration due to gravity is a constant. So it's the same. So in order for weight to be different, it's not the acceleration that changes, it's the mass that changes. So it's really the mass that is much more, much larger for the steam engine than the cat. What I'm saying is, by definition, weight, W, is defined as mass times acceleration due to gravity, 9.81 meters per second. So we've already established that this is a constant. So if you have weight 1, that's going to be equal to mass 1 times G. And if you have weight 2, that's equal to mass 2 times G. So if weight 1 is greater than weight 2, it establishes that because the acceleration due to gravity is the same for each, that establishes that mass 2 must be, mass 1, excuse me, must be greater than mass 2. So in the example that I just gave, that's a qualitative justification that it's really the mass, the difference in mass, that is somehow making the significant difference in the resulting motion of the collision as opposed to the weight. Now, I want to ask you, or Emily, question.
Yeah, I think that's where I was getting a little bit tripped up because I was thinking if it would have any effect on the train, but so there would be an effect. It would just be so minuscule that it wouldn't even show up kind of in the real world.
Yeah, it wouldn't show up in a way that would be obvious.
I see.
Yeah.
Okay.
Yeah, because technically speaking, we'll, as I said, because of conservation, there's got to be some change. But practically speaking, the change would not be obvious like it is with the kitten. It's clearly obvious with the kitten, right? Because I'm so massive, the kitten would not be able to move me, no matter how fast he or she is going in some real way. At least not because of the physical collision. It make me because maybe I get scared. I don't want to get scratched or something, so I move myself. But yeah, so that's what I was. Yeah. Okay, so now I kind of give that result because I just want to get you thinking. So for the next one, the question I really want to ask is, if mass is the thing, or the difference in mass is the thing that's making the difference, and this is a question that you probably were asked before, so there might be an answer that you could remember back from biology or maybe chemistry in high school, but we need to rethink it here because of the law. And the question is, if mass is the thing that's making the difference, what in the world is mass? What is it? Luz, can you define mass for me? What is mass?
Mass, I think it's directly proportional to matter. So I mean, if you say mass, like of course weight, but like how much also like space it takes up, not just like I guess the density. So yeah, that was a confusing answer, but definitely in correlation to how much space it takes up and its weight.
Yeah, awesome, good. That mimics, or reiterates, or it I don't know the word I'm looking for. Recalls definitions that we had, back in high school chemistry class, right? And I think there are two versions of it. One I kind of refer to as the chemist version, and the other the biology. So and you kind of had alluded to both of them there with your wording. So what I remember is that from chemistry, mass is the amount of matter contained in a substance. So that's where that comes from. And maybe from biology, I remember I had this biology teacher in Ms. Caudle in 10th grade. She had a couple sayings that I remember from that. But one is this definition that matter is mass is an object that has volume and takes up space, or something like that. Something like that. And of course, you can combine the two. You know, it's the amount of mass is the amount of matter contained in the substance, which you know, has a non-zero volume and takes up space. Whatever. Yeah, good, right. So yeah, that's basically up until now, up until today, that is the definition of mass that we all were that you were given, and that's what you know. Okay. Well, I think you can kind of intuitively see how the example that I'm giving you is associated with the law of inertia, right? Because I want to ask you, we just established that unless there's an external force on an object, the object is not going to change its motion reasonably or visually. In the case of, let's consider me, I'm the object in question here. When the kitten came and hit me, ran into me, he did apply an external force to me, but I really didn't move in a way that was measurable. Yeah, I did move in, you know, in some way, but not in a way that was measurable. I didn't really significantly change my motion, which was zero. But when the steam engine hit me at the same speed, it moved me along and caused me to accelerate to 1 meter per second as well. You can imagine, like I'm sitting here, train comes along, picks me up, and then I start to move the same velocity as the train, and the train's velocity seemingly doesn't change at all, you know, measurably. So we've established that the only difference in those two things, the external, well, the major difference between those objects, even though they were moving at the same speed, is a significant difference in mass. So somehow mass must be related to the change in motion that occurred in me as a result of the collision. The mass must be associated somehow with the external force that applied on me, and therefore also associated with the change in motion that resulted. So what I'm trying to show you is that somehow mass is associated with the first law, even though there's nothing about mass in the first law. Okay? Now the final question, and here's the rub. Based on what you know about the first law, which I've just stated for you, which object do you think has the most inertia? The steam engine or the kitten? Emily.
I think the steam engine for sure, because
Oh.
it's the least likely to stop. The least likely to stop if something comes in the way. Whereas like the kitten, it doesn't have that much mass to it, and its motion isn't necessarily great enough to affect like how much inertia it has. So I think the kitten would have the least inertia, so it would be the most likely to get out of its state of rest.
Well, in that case, out of the state of motion, and therefore I would out of my state of yeah, awesome. So good. So we established that the train has more inertia than the kitten. And I like what you said because it was least likely to stop, you said. I want to tweak that a little bit. The train has more inertia because since it has more mass, it was least likely to change its motion.
and the kitten was more likely to change its motion, which it did because it came to a stop. Remember, the key in the law of inertia is change in motion, not motion, but change in motion. Now, that said, Emily, since you had a great answer there, I'm going to go with you on this. Can you, if you now have said that the train has more inertia, and I agree with you that it does, clearly you do understand emotion, something about inertia. So can you actually define inertia for me? What is inertia?
Well, I mean, would you like me to define it in a way other than the way it's written on the board, or?
But it's not written on the board. The law of inertia is written on the board. But do you see that nowhere
Oh,
in that
I
law
see.
is it actually that he doesn't say anything about inertia? So why is he even calling it the law of inertia? And by the way, what the heck is inertia? It's not in the law. I mean, it's like when you define something, you don't use a word to define itself. So yeah, I'm calling this a law of inertia, but there's nothing about inertia or mass that's explicitly stated in the thing. So what do those two things even have to do with this? Herein lies why I'm giving this example.
Right.
So can you go for it, Emily? Can you define? Because clearly you do have an understanding of what it is. So tell me, define it in your own words. What is inertia?
Okay, I'd say that inertia is the tendency of an object or person or whatever it may be to resist any change in its motion that's directly proportional to mass and motion, I guess. I don't know. Does that make sense?
Wow. That is absolutely a wonderful definition. You should write that down you always want to try to do it in your own words. That is absolutely correct. Inertia is resistance to change in motion. That's it. That's my definition of inertia. Inertia is resistance to change in motion, clearly illustrated by these examples and your explanation and understanding of what we discussed. So that's the first thing that comes out of the law of inertia, is that we have to define what inertia is. This is explaining the law, but the law is not, it's related to inertia, but it's not inertia. So what the heck is inertia? Inertia is resistance to change in motion, period, full stop. And again, you see that kind of negative implication in there. It's not motion, it's resistance to, and not resistance to the motion. You're getting careful. It's resistance to the change in motion. That's the key. And you actually answered the second question that I was going to ask. You answered it in the context of this because you kind of went on and said something else. But let's kind of separate them and be clear. So if that's inertia, what is mass? Since you're on a roll, Emily, can you go ahead and give that a shot? And you actually did say it, but I want to separate it out and make it as a separate statement, just to emphasize it. So if inertia is resistance to change in motion, what is mass, Emily?
The way I define mass would be a component of basically like a component of inertia that affects its kind of the magnitude of the inertia an object has, if that makes sense. So yeah, I kind of want to say it's like, I want to say it's directly proportional, even though there's not necessarily an equation, but that's like, that kind of makes sense in my head, where it's like if an object's mass increases, its inertia is also going to increase as a result, and same with its motion. I don't think necessarily that how much it increases matters that much. I think it's still gonna make the inertia of the object increase too, whether it be slight difference or a big difference. But so yeah, I'd say direct mass is the amount of matter in an object directly proportional to its inertia.
Yes, that's a very good. The last thing you said, the amount of matter in an object directly proportional to the inertia. Yeah, yeah. And so, yeah, that's it. And what I would say, I can say that even a little bit more concisely with the wording that I've kind of come to over the years, is that just saying that one more time, even shorter, even more poignantly or concisely, mass is a measure of inertia. So if you determine how much mass is in an object, relatively speaking, you know how much inertia is in an object relative to something else. Mass is a measure of inertia, both qualitatively and quantitatively. So as you correctly implied, the proportional nature is implied by that measure of inertia. So what's the upshot here? The upshot is that we now have, prior to coming into this class, we had a definition of mass that really doesn't serve us. Sure, for a chemist, you can see how the amount of matter contained in the substance is specific to the kinds of things that you're going to be doing in chemistry, looking at reactions and stuff like that, because the amount of matter is also associated with the amount of energy. Mass is related to energy, and that comes out maybe in physical chemistry, but that ultimately is, whatever. Kind of with biology, something that has volume and takes up space. Well, like if you got some carcass that's rotting and, it's going to be more stuff associated with that process than something that is smaller, because it's a smaller amount of mass in the volume. There's less mass. So you can see like those definitions are specific to those disciplines and this perspective by which mass will be considered in those disciplines. But you can see now just from this experiment how mass is so intricately related to the idea and to the implications of the first law of inertia, of the law of inertia. But you could also see how those previous definitions of mass, they don't help us at all in understanding the physical implications of the first law. So I feel that we need to redefine mass in the context of our perspective, and this discussion has allowed us to do that. So now when I ask you what mass is, at least for the purpose of physics, this is the definition that I want you to come to mind. Mass is a measure of inertia. Implies the first law, the law of inertia. What is inertia? Oh, inertia is resistance to change in motion. So what is mass? Mass is a measure of resistance to change in motion. And so you can see then in this experiment why I didn't move. I didn't move because the kitten didn't have enough inertia to make a negligible, to make appreciable change in my motion. In other words, my inertia was more than the kitten. My resistance to change in motion was more than the kitten's resistance to change in motion. Therefore, I won out. I didn't move. Not move, change motion. I didn't change my motion, but I forced the kitten, or I made the kitten change its motion. Similarly, the opposite occurred with me in the train. The train's inertia is much larger than my inertia, right? So when we interacted, the train's resistance to change in motion was much greater than my resistance to change in motion. Therefore, the train had negligible change in motion, and my change in motion was quite drastic. So that is the first law. That's really what the first law is about. And that's why it's called the law of inertia. Are there any questions? Emily.
I have a question about how much inertia is affected. And my question is, which one has like a greater effect on how much inertia an object has? Would it be, I know it's very like, there's a lot of measures of it and a lot of factors that go into it, but if we were to just say that mass and motion were affecting inertia, which one has a greater effect on how much an object has?
You mean which between the consideration of mass and motion?
Yeah.
Awesome question. Your question is very insightful. And I would answer that the difference is, remember, I teach concepts, not equations. So the difference that you're pointing to is the difference between inertia and momentum. Because what you're actually doing, unbeknownst to yourself, is you're comparing apples and oranges. Velocity has absolutely nothing to do with inertia. Nothing. It's related, and I showed you in this example. This is why it's a great example. Those objects both had the same velocity and clearly had very different very different inertia. So the short answer to your question is that the only thing that affects inertia between those examples is mass. And not only that, velocity doesn't affect inertia at all.
So even if the kitten was going like some crazy number, like 200 miles an hour, it still wouldn't change. Because I was thinking about what the possibility would be of the kitten actually causing a change in motion in the human. And I was thinking of like cartoons where like animals like zip fast, really fast, and it's like really unrealistic, but they go super fast and they have like smoke coming off of them and all that. And I was thinking that, and like obviously that's very unrealistic, but if it were to have that sort of magnitude of velocity, I'd assume that it would like trip me off my feet because it would be so fast that I would just fall. So if it were to run into me, but if you're saying that velocity doesn't have anything to do with inertia, then that's where I get a little bit confused because I'm trying to think of all the scenarios that are possible.
That's a great example. And I admit it is a little bit confusing. I guess, so I would say the short answer is that there's another quantity that's also involved in this example that I'm not talking about, and it's called momentum. And the thing is, momentum also, and we'll define it here with the second law, momentum actually is dependent upon mass and velocity. In fact, it's specifically defined by those two things. And so you remember I talked about, the fact that there is some change in motion is associated with the fact that the conservation of momentum. So I would say that I would answer that question that the reason that as the speed increases, the momentum actually increases. And so even with the kitten, at a certain point, the momentum will be such that you will have a non-negligible result in the change in my motion. Now, does the inertia of the cat change? No. Does the momentum of the kitten change? Yes. So it's kind of like in this example that I gave, both momentum and inertia are in effect. And I guess, the freight train actually does have more momentum as well because of its mass. But I guess I'm choosing to focus on the fact that of the difference in inertia as opposed to momentum, I guess. But the train would have such a large mass that, you got me on that one. That's actually it basically comes down to what is the difference in momentum and what is the difference in momentum and inertia. And the difference is that momentum is proportional to velocity, but inertia is only proportional to mass. Basically, momentum is proportional to momentum is proportional to velocity, and the constant of proportionality is the mass. Whereas with inertia, inertia is only dependent upon and proportional to, as you said, the mass of the object. So yeah, I think maybe the best way that I could address that is maybe continue on, and we'll get to momentum in this next section and define what momentum is. And then maybe at least intuitively, it'll become a little bit more clear the difference between these two concepts, inertia versus momentum. But you're right, as the kitten's velocity increases, it's going to have the possibility of more effect. And maybe that's the thing I could say. Because, yeah, that's the thing that I would say, is that since we have now defined mass as a measure of inertia, in your example, as the kitten increases its velocity, does the mass increase? Emily?
No, it stays the same.
No, it stays the same. And this is physics for you. Actually, that's not true either. But in classical considerations, we assume that the mass stays the same. Actually, Einstein, and that's the thing with physics. Like you say something, and then 50 years later, you find out it's not true, right? That's something you have to get comfortable with physics. What I'm implying is that Einstein, when they came along with relativity, in fact, the mass actually does change, right? Time changes, it dilates, and as you approach the speed of light, there's time, length contraction, time dilation, and change in mass. All that's happening. And the thing that people don't realize is that it's kind of like what we were just saying now, what you were asking me about when I said the train doesn't change its motion. And then you pressed me and said, well, it doesn't change at all. That's what you were considering. I guess I didn't realize. And apparently all of you were, which is good. But it's in certain conventional classical kind of parameters, we say that it's so negligible that it didn't really change much. But that exists on every level of physics. So when something is moving, we say that we assume the mass is constant. But what we see when it starts to move very, very fast, there's an appreciable change in its mass, its length, even in the concept of time. And it's proportional to the speed. So then, if that's true, when I walk across a room, I mean, proportion is proportion, right? So as my length contracting, is my time dilating? Is my mass changing? The answer is yes. Yes, it actually is, but it's so negligible, so small that it practically isn't. So that's why we didn't catch it. That's why Isaac Newton, I just got on my high horse, my soapbox and, preached Newton up. And I suspect that Newton actually knew this, but there's a lot of things he didn't say because, obviously he didn't talk about calculus. So I have an inclination that Newton probably suspected that there was something else to the picture, but he was living in a time where he didn't have, the technology to actually show it. So he probably just didn't say anything. But I have to believe the guy was so smart. I have to believe that he suspected something was not fully correct with his laws and with, the classical aspect of the way the world was, his laws dictated the world. But it wasn't until a couple hundred so years later that we started measuring these things, and we realized that Newton's laws fail for objects that are very small and go very fast, i.e. relativistic particles. And so therefore we had to develop the new mechanics, modern physics, which ultimately led to the new mechanics, which was quantum mechanics, as opposed to just mechanics. And it's basically just taking classical laws and adjusting them so that they, these corrections would also apply to relativistic particles, but then those corrections would be so small that they're practically negligible, so we don't consider them for classical consideration. So basically, velocity doesn't equal distance times time. It equals distance times time plus some relativistic correction that, when we consider the problems that we're doing, are so small that we just don't talk about them. So really, at every level, this thing is there. So back to the question that I was asking, or that we're pointing out, is that that's the best way that I can answer your question at this point. That the reason that the object will move as this, like my motion will be affected as the kitten's velocity increases, is because its momentum increases. And the momentum is also affecting my motion. And when it was so small, not only was its inertia less than mine, but it was its momentum was below a critical point as well, that it didn't affect my motion. With the freight train, its inertia was large enough, but also its momentum was beyond that critical point as well. You could say that, because I can describe it from that point of view as well, in terms of why it changed my motion. The freight train is not only I chose to focus on the inertia, but you could also say that, make the same argument with momentum, which we will in a minute. So I guess, I know I said a lot, but that's the way, that the most succinct way that I can answer your question, is that as the velocity increases for the kitten, the momentum increases, and therefore the concept of momentum takes over in that collision with conservation of momentum and shows the negligible change. But whereas below a certain critical point, both the inertia and the momentum were small enough such that the effect was negligible in terms of its change in motion on me due to the collision that it has. A lot of words, but I hope that makes some kind of sense, and maybe a little bit more sense here in a minute now when we define what momentum actually is. But so hold that, and we'll come back to it in a minute. So I hope that helped you a little bit. Yeah. So any other questions before we move on to the second law? All right. So let's go to the second law and define it. Now, you probably all have heard that. I mean, it's like the most famous of Newton's laws. So anyone want to tell me what's the equation or the definition of Newton's second law? The law, force law, or anybody know? Someone who hasn't talked today. Mac, you there? You know Newton's second law? Oh no, someone. It was Eric. Eric's here because you don't have a mic. But Eric, can you tell me what's the second law? Eric, do you know? You can write it. What about you, Ashley? You kind of quiet today. Are you there, Ashley?
Yeah, I'm here.
Do you know what Newton's second? Yeah, go ahead.
Isn't I guess the equation related to the second law, F equals ma?
Awesome. Yeah. And most people know that. F equals ma. Can you explain what those symbols represent, what they are? What is F and M? Well, we know what M is now, but can you state it in a sentence like what you did, but like what the symbols are referring to? What is the F?
Force equals mass times acceleration.
Yeah, and what is the definition of acceleration?
The change in velocity.
Awesome. Going back to change, relating it to the first law. The first law is saying when there is no net force, there is no change. Remember, stated in the negative. The second law says that when there is a net force, then there is a change. A change in what? A change in the motion. Remember, motion is velocity. So, and velocity is motion. So what the second law is saying is that if you have a net external force on an object, the motion will change. The motion will change. So we call it the force law. The net external force on an object is proportional to, well, Isaac Newton says something, proportional to the rate of change of the motion, where the mass of the object is the constant of proportionality or something like that. We'll just say the net external force on an object is equal to the mass of the object times the acceleration of the object. Yeah, so we're making some progress with physics now, because even though there's something that you knew and had some idea before coming to the class, we can be a little bit more specific about what we know about this. We know acceleration is change in motion. We know mass is a measure of change in the mass of the resistance to change in motion. And formulaically, we can write that the net external force on the object, right, is equal to the mass of the object times the acceleration of the object. All right, so that's the basic definition. And a simple explanation is we've already investigated plenty of, we've looked at motion already, and we've seen examples where the first law is definitely in effect. But now, as I told you, we can explain a little bit more about it now that we have this. A couple of things in point. I drop an object. The only force, like when the object is in my hand, it's not accelerating. So the first law must be applying. Why? Because the motion isn't changing. So right now, there's basically two forces on the object: weight down, and I guess I would say it's not so much a normal force, but it's a force of contact, and that force is up in my hand. I'm holding it. So that force that I'm holding must be equal and opposite to the force of gravity. Why? Because the motion is not changing. The net force then is zero. When I drop it, the net force is not zero. Why? Because the only force on the object was gravity. So since there was a net force that was non-zero, that force started to accelerate the object. That's this law. That's free fall motion. The only force on the object is the force of gravity. Yeah, so you're at your car, in your car at a stoplight, you're not moving, all forces on you are zero, you gun the accelerator, the engine force is going to start to move. Now, there's also a frictional force at the tires on the road. We'll get to that, maybe tomorrow or next week we'll start talking about friction. But basically, your engine force is larger than that. So therefore, there's a non-zero net force in your direction of motion. So therefore, you have acceleration. Couple quick properties of this law. The units are measured in newtons. We pay homage to Isaac Newton by giving him, naming his we named the unit after him. And we have also looked at the units of the basic units of mass and acceleration. We know that mass is in kilograms, acceleration is meter per second squared. So a Newton is equal, which is abbreviated capital N, is equal to a kilogram meter per second squared. Force is a vector. It gets its vector nature from acceleration, so it has both magnitude and direction. It's a vector quantity. What else? Yeah, I don't know. Those, yeah. It abides by superposition. So we'll see, like when we have several forces on an object, in order to add them, we have to add them vectorially. I told you we'd come back to that, compared to what we were doing with relative motion and kinematics about, in chapter, I guess 3 it was. And we'll have specific examples where we show how to handle that. We'll review the vector analysis rules again. Yeah. Now, I promised you that I would, there's actually 2 versions of Newton. In fact, this was not the version that Isaac Newton actually wrote down when he wrote that second law. But it's the most practical version, and it's the one that we now conventionally teach first when we're presenting Newton's second law. But there's another version of this law which allows us to introduce the concept of momentum. So let's take that and do a quick derivation right now where we show that. Now, we know what acceleration is. You just defined it for me, a change in motion. And quantitatively, we use that to, in the limit as delta t goes to 0, the time we're considering the change goes to 0, we can define that in the limit of that change, we can define a derivative. That is to say that we can say that the velocity of the acceleration of an object is defined as, we'll do the magnitude. It's defined as the time rate of change of the velocity. Now, yeah, right. Time rate of change of velocity. Now, if I take that definition and substitute equation 2 and equation 1, then I can write Newton's second law in terms of that definition of acceleration, that net external force is equal to mass times the time rate of change of velocity. Now, I'm going to emphasize the temporal dependence of velocity. Now, normally, that's the way that we would leave the second law. Because normally, in our case, we assume mass is constant, it's not changing. But mass can change. A great example of that is a rocket, a conventional rocket. Conventional liquid fuel rocket, most of the mass of the rocket is the liquid fuel. And as the rocket accelerates, burns up, accelerates, it's using quite a lot of its fuel per unit time. And when it's used all of the fuel in one stage, it jettisons that stage because it's no longer useful. So clearly, its mass is changing quite drastically. And, we could come up with some other examples, but the point is that mass, the fact that mass is constant is a special case of consideration that we do at this level of physics. But in general, mass is also can be time dependent. And if we assume that it's time dependent, then we have to incorporate it within, that derivative from a mathematical point of view is just an operator. And we can incorporate it within this, within this operator whenever it is relevant and pertinent to do so. All right. So what I'm trying to say is that, if mass is time dependent, then we can say that this constant mass goes to a time-dependent quantity that I can emphasize there. So if that's the case, I've got to take this guy on the inside. So let's do a quick aside here. Let's say that, well, let's just do it like this. Let's say, if I take it on the inside, then I have a time derivative of a quantity of mass per unit time times velocity with respect to time, that is, not per unit time, but mass with respect to time times velocity with respect to time. In fact, here's where I can do the side, is that, you can see that this must be a true statement because, or that I can do this because if I take the derivative, so the derivative of m of t v of t is actually equal to m dv dt plus v dm dt. Well, if m is constant, then that term goes out and I'm just back to m dv dt, which was this guy. So clearly this can be a true statement. By the way, if mass is not actually constant, this term actually has a name. Does anyone know what this is? It actually applies to the rocket problem as well. That was a great example to come up with. What is velocity times the change, the rate of change of mass? It has a name. I think there was there a couple aerospace engineers or people going in, they may not be in class right now, but are there any aerospace engineers in here or pilots or anything right now in class? I think there was one on the first day. You know who that was. Well, this term here, sometimes I do the rocket problem, sometimes I don't. It depends on time. Usually in the short semesters I don't. But it's actually a derivation that can be done in class. It's to derive the rocket problem. But it turns out the concept of thrust, that's actually what this is. Thrust is a force term, but a specific type of force term where the mass is changing. V dm dt. We don't really deal with a lot of thrust here in this level because we assume for the most part that the mass is constant for our object. So that's just a little bit of an aside there. But even if the mass is not constant, I can still take it inside here. It just turns out that when I take the derivative, it's just going to be a zero value over there. So I can still define Newton's second law in terms of a change of both, the product of mass and velocity. So from equation, well, we'll take it from here. So we can say that the net force on an object is basically equals to the time rate of change of mass times velocity. And yeah, so in our case, we can still just emphasize that the velocity is only time. This is a constant, but still inside. So here's where we can define this thing on the inside of the parentheses as a separate quantity itself. And as it turns out, most of you might have known, I didn't ask you, but that is what momentum is. And that's where we define it. We say that, oh, this isn't a unique quantity because it has properties and other things we'll talk about. So we're going to define it as a quantity within itself. It is the momentum. And we use P, the symbol P, to represent momentum. Most books do. Small p for smaller objects, capital P for systems of objects, the momentum comprised of system of small objects. And it is defined as 3 equal signs, the mass of an object times the velocity of an object. Velocity, not speed. So therefore, momentum is a vector quantity where the mass is the proportionality constant between the quantity of momentum and the velocity. Well, yeah. So this is, and in fact, there are types of momentum. This is linear momentum. Now, we will come back to this later when we get to rotational motion. There's all kind of properties associated with momentum that we'll discuss, but here I just want to define it. Mass times velocity. So we can then rewrite, the final step is to rewrite Newton's second law in terms of momentum. And we can say that Newton's law, another version, a different perspective, is that the net external force on an object equals the time rate of change of the momentum of the system. So equation 6 is actually another version of Newton's second law. It is a statement that is tantamount to F equals ma. So from this point on, when I ask you what Newton's second law is, this statement is a perfectly valid way of answering. You can say that Newton's second law is states that the net external force on an object is equal to mass times the acceleration, or you can say that the net external force on an object is equal to the time rate of change of the momentum of that object. Either one of those statements are true and basically are the same statement. Now, in the last 2 minutes before we leave, you can see, back to your question, Emily, what the difference is in those two examples. That although the inertia doesn't change, so momentum, the example that I gave, it could be described I use it to describe inertia, but I could do the same thing and it would almost be the same argument as by justifying it with conservation of momentum. However, whereas I couldn't really quantify that with talking about inertia, I couldn't quantify and show the difference in velocities. With momentum, I will be able to do that. And we will actually do that when we get to collision problems in a couple of chapters using conservation of momentum. So I guess that's the confusing thing, is that you could describe those examples with either the concept of inertia or the concept of momentum, depending on what you're trying to illustrate. And and that as the cat's velocity increases, his inertia definitely doesn't increase because his inertia is only dependent upon and proportional to the mass. And within classical, with classical considerations, if we assume that the mass doesn't change as his speed increases, then his inertia doesn't change. But because of the momentum is proportional to velocity. And so as the velocity increases, the momentum increases, and momentum is something that can also impart impulse force to external force to something and cause it to accelerate or to move. So does that help with your confusion with that example that you gave?
Yeah, I like seeing how everything's related to one another. I think that really helps, and it kind of makes, like, it brings the whole picture together. So yeah, to me, it's really interesting how like everything's related when it comes to physics. So it's nice seeing that as we progress through the course.
Yeah, I think that's a paradox, right? It's like everything is related. It's like, we talk about nonlinear versus linear mathematics and concepts. But the thing is, nonlinear, which is where our reality really exists, it's all fake. It's nothing's nonlinear. Everything is related, which means there's no such thing technically as so I said nonlinear. Is that the word I'm looking for? No, it's not. I'm thinking of, sorry, I'm drawing a blank here. Well, maybe. I'm just having a brain fart. Well, the point is, yeah, that everything is related. And whenever we can kind of make sense of certain concepts and physical phenomena, we're just relaxing the aspect of that phenomena that's related to other things so that the mathematics is simpler. Classical physics is a good example, right? In fact, when we first came up with classical physics, we didn't even know that those other things were, because that's the whole, that in fact, what you just said is actually the difference between, you probably heard it a lot. You know, this course is called classical mechanics. What's the difference in classical mechanics versus quantum? I mean, there's a lot of difference, but I'm talking about qualitatively. What is the difference? Sure, we can quantify it because of, and I did that some way by giving you that example that I gave, but just qualitatively, why is it necessary to categorize everything as classical versus modern physics or quantum physics? It has to do with basically Newton's one of the fundamental postulates that Newton made. And that fundamental postulate is literally what you just said, or the opposite of it. Nothing is connected. The only time that things interact is when they are physically in contact with one another, which means that when they're not in physical contact with one another, they're absolutely not affecting one another. That's the difference between classical physics, where there's mechanics, thermodynamics, electromagnetism, versus quantum. Once we went down to the quantum level, in addition to having to change the quantitative aspect of that, there's other qualitative implications. And the implication is what you just said. Everything is not only related, it's affecting everything in every minute, physically affecting things. But it's affecting it through fields and waves and things that we couldn't detect whenever classical physics was created. That gives rise to, I guess nonlinearism, a nonlinear world, meaning I can't just sit here and determine the velocity of an object for a force that I hit it on. It's not going to be correct. Why? Because every other object out in the universe is also affecting it. Everything, the sun, all the stars, everything around us is because they have force, and force doesn't dissipate. When we get to the universal law, we'll see it doesn't dissipate until it's at infinity. Well, those things clearly are not at infinity compared to us, which means that they're having an effect on us. But when you consider it from a classical point of view, you throw all that stuff out. Why? Because it's negligible based on what the values that we need to use, and it's not making a difference. So for all practical purposes, we say that it's zero. Those forces are not affecting it. But in reality, they aren't really. They are affecting it, which means that what we're calculating isn't actually correct. And yeah, that's one of the realizations you begin to have, is that, and you see how complicated the world really is. But fortunately for us, we can, those complications, from a very limited three-dimensional space-time perspective, are they're not affecting us in ways that we're aware of. I'll put it that way. And so for practical considerations, our everyday lives, we can go on about our business and assume that everything is linear and classical in ways, for the purposes that we need to do so. Yeah, pretty fascinating stuff. Well, let's go to break right now. We got go to lunchtime. Third law is the law of action and reaction. which I affectionately refer to as karma. Oh gosh, it's here.
How did
Oh.
this relationship between the two of you?
I didn't miss it. So they were just saying it's coming up next before they went to commercial.
To the point where it is now.
So action and reaction. Oh, by the way, you can hear me, right? Everything's good. Someone give me a thumbs up. Yeah, good, awesome. So the what? Action reaction, yes. Karma. It's simply stated, the law says that for every action, there's an equal and opposite reaction. I'm not going to write it just in interest time. You can write it down. Good. For every action, there's an equal and opposite reaction. So if I lean against this, my desktop here, and I apply a force on the wall, then the wall applies a force back on me. That's it. That one simple rule has some really interesting implications with regard to the properties of force. And again, a really nice, just as another example to be complete. If I have this object and I sit it on the table, well, the object applies a downward force on the table, just like you sitting on your chair, right? But then the chair applies an equal but opposite force on you. Now, again, two implications come out of that are universal properties of force, full stop. And those properties are all forces everywhere in the universe come in pairs. All forces exist as pair forces everywhere in the universe. That's the first thing to be aware of. The second thing is that pair forces always, without exception, exist on different objects. That is, pair forces will never, ever exist on the same object. So just because you have, I'll just leave it at that. Pair forces always occur on separate objects. I think I might have, from that blurb I saw before it went to commercial, I think I might actually know. I don't know what they're saying, but I know what they're referring to. I mentioned when I talked about UFOs on the first week, I said something about the TikTok or Tic Tac, I think is what they call it. Oh, here we go. I'll let you look.
UFO sightings were officially called unidentified anomalous phenomena, or UAP, with eyewitnesses testifying, not researchers or enthusiasts. A former fighter pilot and a retired naval commander who said they saw UAP with their own eyes were on the hill. Also under oath, a whistleblower, an Air Force intelligence officer of some 14 years. He has been tracking years of UAP accounts from members of the military. Retired commander said people need when you read these reports, as I have done, and they give a range of possible explanations and no certain answers, ranging at the outside to this distant possibility of alien life, but also to the possibility that this is advanced military technology by, say, U.S. adversary, Russia or China. You've been deep into this for some time. What is, in your view, based on the evidence? Well, you know, it's hard to say what most likely is. Only 6% of these ones actually didn't have an explanation. And then even some of these like that, you know, that video right there, that came out, people were like, oh my God, this thing is moving away, can't understand. And the NASA panel showed the got 40 miles an hour, right? Which is faster. I can go that fast rolling down the hill on my bike. So, you know, there's a lot of things that need time to be done. And what we can see here is that they have anything to do with like somewhere else. I think that's something. But, you know, the way when you can find people that can understand. So at this point, is that it could be sensor noise in effect. You've got a lot of highly sensitive instruments in the cockpits of airplanes that they're picking up something or reading something different. Is that something that is considered a likely explanation for some of these? And again, right, like you noted, they don't have an explanation for absolutely everything. Right. And then the telescopes, you know, that's, you know, that's a very thing. Study. Science is about, you know, Professor Adam Frank, thanks so much for joining us. Spacey openly weeping in court as a jury acquits him of sexual assault charges. We'll go live to London.
Okay. Well, that was a little bit of a I didn't didn't know what was going to be said. I hadn't seen anything really about it. I thought they were actually going to show some of the testimony in Congress, but just a few minutes of commentary about that. What did you think about anyone's Sandra? What's your point of view about, I guess, UAPs is what they're called now, and in general, and just maybe I should actually do a discussion about it. Maybe that'll be next week. Do a discussion on that. So there's a lot of fodder there, but if you feel comfortable, just commenting about your point of view about that. Have you ever seen anything that you thought was unexplained? And about his the professor's response there to the topic of UFOs or UAPs. Susan, are you there? Simone? Sorry, Sandra. Sorry, Sandra Simone. Sorry. Okay. Oh. Internet is slow. Okay. All right. Well, while you're doing that, what about you, Jorge? Are you there?
Oh, hear me?
Hey, I can. Yes.
All right. I couldn't really hear the video. It's hard
Oh,
to
really?
hear.
You couldn't? You
Yeah.
couldn't hear the? Oh,
It was like very distant.
Oh man.
Yeah. But if you
I
give me like
wish.
a summary, I tell you like my thoughts on it.
Okay. Was that for everybody? Not everybody. You couldn't hear. What about you? Anybody else comment? Could hear? Emily, could you hear?
I could hear it from like far away. I think it's because it's connected to your AirPods. So when you left, it like, if that makes sense, like.
Oh yeah. Okay. Okay. Yeah. Oh, that's unfortunate. Yeah. He. I mean, if I say it, it's going to kind of probably cover my point of view about which I wanted the more objective from you. Yeah. Well, basically, they just said that he said there was no conclusive. They were just asking him. I guess the reporter asked the professor if these are credible reports, and they were the video that they were showing was the Tic Tac. That Tic Tac is actually, maybe I could find. Sometimes people post things on CNN pretty quickly, so let's see if I could find maybe either that interview or. And because actually they were some earlier today in some of the other cycles. So hold on a second. Okay, so this is actually the guy. I don't know if it's today. Is that today? Yeah, 22 hours ago. So yeah, here you go. So I did find it. That's interesting, man. This technology is crazy, man. So this is not the same video report of that, but it's the same incident and same news cycle issue, and I guess so different. Don't know if it's CNN or whether they had this guy, but whatever. It's about the recent testimony on the Hill, and I guess this is the pilot. So here you go. And why don't we hear it? What do I have to do? What do I have to do?
And you're all kind of laughing. What is that? It became very serious for you. Do you have any idea
So first of all, before I let that play, I couldn't tell whether you could hear it or not, but
I heard it.
you could hear the video. Okay,
Yeah.
so I'm gonna go back and let it play in its entirety.
All right.
Okay.
Serious for you. Do you have any idea of what that was?
No, I can't hear it. No, I can't hear it.
Operating off our coast, and when we can't.
No, I hear it. And now it's gone.
Okay, gotcha. Just trying to.
When you hear UFO, your mind goes to that conversation with aliens looking at you. We don't have enough information to say where these objects are originating from. That's what we're trying to do. We gather more information.
I don't know any way to get your echo out.
See the video and you're use that. It's very serious for you. You have any idea what that was? We don't. To your point, being able to identify a fire is not a part of even everybody. We're out there looking to identify who's operating off our coast, and when we can't ascertain who the owner is or their object, that's a big national security issue. When you hear UFO and even UAP to some extent, your mind goes to that cultural conversation about aliens and things of that nature. We don't have enough information to say where these objects are originating from. That's part of what we're trying to do. Gather more information and take a hard look at the data in a serious way. So we can determine if there are security concerns that will pop up.
Okay.
You see that video and you're all like, wow, what is that? It becomes very mysterious for you. Do you have any idea what that was? We don't.
All right, so we're back. Well, that wasn't much either. And honestly, the article that I was, the thing that I had on maybe a little bit more glorified, but basically, similar kind of thing. We don't have enough information. Gathering more information, science can't be certain. And the two men on the interview lean more towards skepticism than possibility. Which is there's no proof. No one has any proof that we have seen. I mean, I think that some people have some proof, but hasn't been presented. So based on the fact that there's no presentation of concrete evidence, that's all you can say. It's really just comes down to speculation, which is kind of what they said. And but it's really interesting, like again, I've shown you how we've talked about how much that we have evolved in 40 years. And I've always been interested in these kind of things. Even before I was in college as a teenager, some of the shows were like, there are a couple of shows that were around. Now there's an infinite number of streaming possibilities and content. But back then we only had 3 networks, and on the networks, only a few of them, well, generally the networks didn't, but there were a couple of other private channels from we called educational television, where they were basically in there was actually 4 channels. There was 3 networks, and then there was a national independent channel, which looked differently depending on what region of the country you were in. But on that station, there were a lot of programming that was independent, what we now would call independent programming. And though that's where you would find shows like In Search Of with Leonard Nimoy, who was Spock on Star Trek. There were some people that were independent, but they were kind of large companies, and they would put out programming that's similar to programming that you now see on the History Channel, like Ancient Aliens and that. It was like the precursor for those kinds of shows. So one was called In Search Of the Truth, supposedly, or In Search of Information, but just In Search Of, hosted by Leonard Nimoy. And then there were a couple of others. And, you know, I would just drink those shows up. And that's where you would see things, people talking seriously about the possibility of sentient life and that sort of thing. And from that time until this, basically what you heard the official person there, the Navy pilot, say is the same. We need to have more information, right? As we have certainly gained more information with all our technology, still, you know, we need to have more information. So you would think that there has been something that if you kind of compare the technology that we've gained since then, you would think that we would have a little bit more insight to that than we did 50 years ago. And my logical mind tells me that we do. It's just is not being, that information is not accessible. That's just my opinion. But I don't know. I have no proof. You know, it's just an opinion. And as far as I know, no one really does. So that's just, you know, that's I guess my take. But you know, it'd be nice to kind of hear your point of view about that sort of thing. And so who was it? It was Jorge. Yeah, if you don't, since you know, you said you could hear that, would you feel comfortable making a commentary about your perspective about the perspective of sentient life? And go for it.
I think it's hard to say based on the video. It's hard to say what it is because they don't even know what it is, and nobody knows what it is, and it's kind of hard to really pinpoint if it's like some extraterrestrial thing or some like other country maybe. But it's hard to have proof these days because like that video could easily be made up by someone. We don't know. We have no idea because it's so easy these days with the technology that we have to just create anything. And I feel like it's really hard to find the truth. But I feel like possibly it could be from an unknown source that's new to us. That would be cool. But yeah, I agree with what the Navy, the military person said. It's hard to know off the bat. I feel like most of the time with the UFO sightings and things like that, we just never know what it is. Like I don't think there's ever been a conclusive like report of what someone found and they like definitely know what it is, because I'm pretty sure they never found out ever. I don't think so. That's my take.
Yeah, I think that's reasonable. I think that's a reasonable response. You know, one thing I would say, it jogged my memory of one thing I did find interesting in the commentary that you couldn't hear for the CNN report is this idea of dichotomy. And it's something that kind of is a pet peeve for me. So I always kind of try to identify it when it pops up, because they presented it in the same way. They said, okay, well, there's the possibility of the fact that this is an alien technology, or aliens alien technology, implying that aliens are driving it, because you question, is it actually extraterrestrial life? Or is it just advanced technology of another nation that could be our enemy? So that's what I mean as a dichotomy, either or. And we see that done in politics a lot. They call it false dichotomies a lot of times. And it's really interesting because it's something based on like psychologically how to manipulate, whether consciously or unconsciously, how to manipulate someone to your point of view, because you kind of create this situation as if those are the only two options, right? And the reality is, and this is something that is a characteristic of science, it's in symmetry, it's a characteristic of the symmetry, like, and also therefore the universe. There's no reason that the universe says both can't be true. It can be extraterrestrial technology, and it could also be a nation, that has developed technology that is our enemy. And you might say, well, how? How in the world? What are you talking about? Well, and this actually, my personal belief, I think that what I'm about to say is actually more closer to the truth. Let's assume, for example, that all of these things that all of the major things you've heard about in UFOs is actually true, starting from Roswell. Because actually, you know that, and I'm sure you probably have if you've seen any show on it, the first couple of days, the US government, right, the Air Force, like this guy was in Navy, they actually reported that it was actually extraterrestrial, a craft that had been confiscated. Maybe the first day, I don't know if it's 3 days, but then either the second day or the third day, they came out and refuted that and then gave what ultimately felt like a plausible explanation to the public that it was a high altitude air balloon that had crashed. And that has been the official story, as far as I know, ever since. Now, what if they were lying? What if it actually was a UFO, right? And then initially the point of view was, to announce it to the public, but then for whatever reason, and there are many ways you could justify what the reasons would be that are very sensible, they pulled it back. Once you do that, then from that point on, you've got to maintain that veil, that lie. And you might say, well, why would you do that? Well, because of obvious implications. If you really think about it, it changes everything. And when I say everything in terms of national, like in terms of our nation, you're talking about defense, you're talking about economy, you're talking about even philosophy and religion, right? All that stuff has to be rewritten. And it kind of destabilizes society. It does. And I don't know what will happen, but certainly what could happen is it destabilizes everything, right? So this is just a thought experiment. I don't know that happened. I'm just speculating logically. And I think it's a very reasonable thing so if that did happen, what would translate after that, right? Well, what they definitely will do is reverse engineer that technology, even as they're saying it doesn't exist. And as they find more technology, more UFO, because if one fell, another's going to fall. And also there is this consideration of defense, because ultimately, at least from our Western point of view, that's always the first thing, money and defense, defense of what we have, of protecting our money and our and trying to establish more. So and that was the height of the Cold War, actually, right? So if it's falling down here, we don't want the Russians to know. We're going to reverse engineer. It's going to give us a advantage in the Cold War, right? Now you scroll forward. I guess that was what 70 years ago, something like that. That's still where we are, right? But when you see a technology like that, the third option that I guess I'm trying to imply is that generations of reverse technology now is being realized because there would have been much success with that. So what you saw there could actually be alien technology that has been successfully reverse engineered, but it's actually a human being flying it. That's also an option. That both could be true. So just because it actually is advanced technology that was made either by us, because it could be a false flag, it could be us flying it. That's the other thing. There's reasons that these ideas of false flag operations, which has become a popular term now. There's strategic and defensive reasons why a country would actually do that to itself in order to be able to manipulate a political or a defensive position or whatever. That's also something to consider. But the point is that yes, it actually could be a foreign entity, a foreign nation with highly advanced technology that we need to be aware of. But that in no way implies that it's also not alien technology that has been somehow accommodated and reverse engineered. So the idea that it's one or the other is absolutely not true, in my opinion. They both could be true. So it's not a matter of deciding one or the other. And when you begin to think like that, you get any kind of logic class or, a military science or even politics, in terms of diplomacy politics and seeing how these models that people make for thought processes, like when you, because that's how a lot of these people think, right? At that level, there are these protocols for how to establish responses to proposed or possible dangers, like invasions of a foreign country, invasions of whatever. And so, or even with politics, how to, when you're dealing with someone like Putin or, the possibility of negotiating for peace in a war, I forget what they call them, but there's these, you basically kind of, it's like, three-dimensional chess, right? You play out all the different possibilities of things that could happen and then try to come up, 2 or 3 levels in. And now they can do it with computers, right? Like you can do it several levels in and try to come up with response scenarios so you go into that situation prepared. But once you start to do that, you can actually use that to actually manipulate people for the outcome that you want, right? So when I'm looking at like a response to this from something, like a video or a TikTok, I have begun in recent years, like the past 10, 15 years or so, to kind of really think along those terms, that it may not be, there might be much more to the situation than what we're presenting, than what's being presented to us. And so why is just that position being presented to us? Because the idea of a dichotomy, I mean, that's actually simple. That's not even very complex psychology. But the fact that they do that and that it's being allowed to being presented in that way tells me something, right? So anyway, just maybe it is something that might be better put to. I don't want to keep more class time on this. I want to try to get some of this done with the second law or the third law and get into a problem or two. But this might be better suited for a discussion, a weekly discussion where you can maybe figure out a way to kind of present this in a way that it would be nice to and appropriate for you to respond in a way that is is constructive. But I just want to kind of share that with you, that point of view, because I think it's a little more comprehensive or point of view about the possibilities of these things and why we see a lot of the same responses, the same type of, like you could take that response and you can go back 30 years and find something similar and it almost be like like they're reading a script, right? Just doing it differently. And even with the video that the CNN report that you couldn't hear, it basically kind of was the same thing. So I just once you begin to see those patterns and you see them over a period of years, but I think it just raises questions in my mind as to how is that there has been no progress or no progress in understanding when we've made so much progress in other things. So there's just a lot of things a lot of things we can discuss about the implications here. But it is just discussion. I think it's important to have the discussion, at least open your mind to that possibility, and have some kind of idea about what you think about it. Yeah, so I don't know. Anybody want to? Pretty long-winded on that. Hopefully, I didn't bore you. But would anyone like to make a comment before we get back to some physics here with third law? Who hasn't commented today? Let's see. Ishan, how are you? I think you weren't here this morning earlier, unless I overlooked you. How are you today, Ishan?
Yeah, hi. Good afternoon. I thought it was really interesting, like the UFO stuff. What I think is like kind of interesting is how everything gets like politicized. I think it's like some people think it's like a people versus government thing. Some people think it's like like an across the aisle thing. But yeah, it's something that like fascinates me. It's also pretty interesting that like it's one of the few like also sort of uniting things amongst people. Like people think there's some like big conspiracy with like UFOs and stuff. I don't know. I thought it was just like pretty interesting that like this is like one of like the huge like social phenomena that like people can just like get behind. But yeah.
Do you think there is some sort? Because I did kind of imply conspiracy when I gave that scenario. What do you think about the conspiracy aspect of the dissemination of the information?
Yeah, I think there's so much that can like explain this that maybe we don't even know about. That doesn't have to be like other life. Maybe there's some like other like physics thing, maybe some sort of like a refraction of light or something that we don't know about. But like I'm not opposed to there being something out there, but I think there are probably other explanations for most of like the so-called like sightings and whatnot. But it's pretty interesting.
Yeah, I wouldn't disagree with that. I think I think you're right. I think there are, because we have to be so careful, and there's so much phenomena on the earth itself that is just so weird, and you find out that it has these things have explanations. I think other thing that they did say is that of all of the sightings and things that we've seen in this report, 6% of the reports it's only 6% that are that even the government doesn't have explanations for. And that doesn't mean that there are UFOs. It does imply extraterrestrial life. It just means that they don't, maybe it is some physics that we don't understand, or, maybe it is something associated with extraterrestrial life. I think that you have to be objective in approaching that, and and I think that's very important. And yeah, and it's hard to know what is true and not true. One of the other things, and this again is just kind of my own logical point of view. I do lean toward the possibility of sentient life elsewhere, and it doesn't really have anything to do with UFOs and stuff. Things that we've seen. It really just has to do with logic. And the idea of space and time. When you actually begin to consider, and now we can certainly much more than we did when I was a kid. We have these telescopes up; we can see pretty far. We can investigate these. It just, the universe is so unimaginably large. And even when you just constrict it to the Goldilocks zones within solar systems and within, the solar, and when you consider all the solar systems and galaxies and all the galaxies and clusters and all the clusters and, in the universe, I mean, I don't know that I can't rattle off the numbers right now, but the possibility of the number of planets where there could be life, it's basically unimaginable. And that's just in one instant of time, okay? When you then expand the age of the universe, and that life could, have been created and then dissipated, for whatever reason on a particular planet or whatever, it almost becomes an infinite possibility. So if there is no life anywhere else and never has been, what that means is that life on this planet, in all those possibilities, in all the time of the universe, the only time life has evolved to the point that it's sentient to the manner in which we are sentient, it's just once. That just makes no sense to me. Like, why? Why, when we see so much symmetry and repetition in the universe, why with this issue, would the universe pick just this thing out to say, oh, we can only do that once? It just doesn't make sense to me. There's nothing in the universe anywhere else that behaves that way. Nothing that we have seen. And that's science, right? If it's done once, it's done someplace else, some way, somehow. And you got to remember, like, I'm not even talking about this, sentient life doesn't have to, evolve with, carbon-based mammals. I mean, it could be reptilians, silicon-based reptilians. I mean, I don't know. It, like, doesn't just have to be the way we're doing, we are. It could be in some other form. But it's not, but consciousness, in other words, only manifested itself in all of that time and in all of that space, just with the way it has happened through us. I just can't accept that. And again, I don't have any proof, but it just doesn't seem reasonable or logical or consistent with any other pattern that I know of that we've seen in the universe. Just that alone makes me lean toward the fact that there is life, just, as sentient somewhere at some time, and that just based on the symmetry of the universe. But, I can't prove it. I don't have any definitive proof. But, it's the kind of thing like when Columbus was looking out, at the ocean, right? It looks like the ocean drops off, like it looks like it stops, and the plane, boat goes over and it went over, like it's not there anymore. So it dropped off the face of the earth. Now, right now, we're saying that seems crazy, but it didn't, 300 years ago, 400 years ago, right? People thought the world, I mean, some people still think the world is flat. There's Flat Earth Society. So from that same point of view, what caused this dude to be able to go out there and not be afraid he was going to fall off? His logic and his intuition and symmetry, looking at other things, thinking about the possibility that if I have this ball and I look at the edge, it looks like it drops off. If I turn it around. So there are more possibilities. Yeah, the earth being flat is one possibility. But based on the evidence, the empirical evidence that you have, there are other models that fit that possibility. So that's what I'm trying to say about this idea of dichotomy versus, some other plausible explanation. That's why, to me, the fact that they could be both true is a plausible explanation. And my intuition leads me to that. I think just in the way maybe Columbus's intuition led him to feel that, maybe I could go over and test this thing and I'm not going to fall off the earth. That's what science does. That's how we progress, in my opinion. Read the comments here. I feel like this comes up so often, like these situations. Yeah, there's not. Yeah. I saw a show at National Geographic where my painting, or many paintings back in the day, paintings from back in the day in the background. Yeah, looked like the UFOs and made people think. Yeah, I've seen those paintings. I think Botticelli, the Birth of Venus, and one of the Annunciations. I think it was Raphael, and you see this like the Annunciation is the painting. I don't know when you're talking about, the one that they show all the time. And there's this thing that looks like a flying saucer, and of course, in the Bible, with Elijah seeing the wheel within the wheel, all these things. There's many, many examples of these things that are other explanations other than, and seemingly to me plausible, other than what we've been, what is going down as the official record. So it's there. When you start to look around, it's all over the place, all over the place. So, I don't know. I mean, I think that at the very least, I think it's important to acknowledge these possibilities, even though, I certainly can't say one way or the other. But I can certainly have an opinion and at least just say and justify where my inclinations lead. And just like a person who's a skeptic can say the same thing. So, I guess that's about all we can say about that discussion at this point. But yeah, I appreciate you indulging that and me taking class time for that. But I thought it's relevant because, for obvious reasons. So, yeah. Well, we got about 30 minutes left, and that's enough time for me to get through the third law and to push on to maybe outline a few examples. So let me take a minute here and come back and do that. Okay. Yeah, so the third law. So the properties, I shouldn't, yeah, it's here. So these two properties, all forces occur in pairs, and all pair forces that exist must exist on separate objects. So let's have an example of that to illustrate. Oh yeah, and the formula for the third law, before we do the example, it's kind of the least most much. But there is one. Consider two objects. Let's say there's two massive objects, maybe two asteroids out in space, near one another. So you have asteroid 1, which has a mass of math 1, and you have asteroid 2. So that's M1, and then asteroid 2, M2, and they are a distance r apart from one another. Yeah, so we haven't discussed gravity quantitatively. We will, of course, but we could just say, well, we have actually. We've now discussed it in context of the first law. We haven't discussed the universal law, but whatever. There's forces. They apply force one on the other, and according to this law. So now I was showing you the example of a contact force where things are in contact. But this is an example of a force that's not necessarily what is not a contact force. It's one of the fundamental forces, but still it abides by the third law because even though their masses are different, and this is the brilliance of the law, the force between them is the same. And we'll talk about why that is when we get to the universal law. I don't want to go there right now, but just based on the third law, that must be the case. That we'll call this force the force of 2 on 1. So I'll refer to that as F2, 1. And this force is the force of 1 on 2. Force F1, 2. So we can see here the example of pair forces. What we're saying is that whenever these objects come in proximity such that the force appears on one, its pair force must appear equally in magnitude at every point and in a direction opposite that of the initial force or the force on the first object, and those are pair forces. And so from this, we could write down an equation representing the third law that F1, 2 equals negative F2, 1, or vice versa. So this is representative of the third law. And in terms of the magnitude, we might say this, that the magnitude of F1, 2 equals the magnitude of F2, 1. So, yeah. Now, an example. Demonstration in class. What do I do with my... So I just had a small blue box. Did anyone see where I put it? Grabbed it, and then I decided to put the law instead. I thought I put it right here somewhere. Wow. Must have dropped off somewhere. Well, I guess I don't have to use the blue box. Turning away. Well, that's so interesting. Okay. I'll use instead of the blue box, I'll use my silver ball. That's a mass. The mass is sitting on the table. Can someone tell me what forces are acting on that mass? Ashley, how are you today? Are you there?
Yeah, I'm here.
Okay. So we have this ball, this mass, sitting on the table. What forces are acting on that ball? And do you know? Well, the ball has a mass of m. So if it has a mass and it's in close proximity of the Earth, there's at least one obvious force that must be acting on it that I could determine if I put it on a scale. What force is that? What do we call that? Are you there, Ashley? Oh yeah, okay. All right. Ishan, you
Would that be gravity?
go ahead. Yeah. So there's a gravitational force. What other forces on the object, Ishan?
Sorry, I think you cut out when you were describing. I wasn't able to catch most of it.
The question was, what other force are you just? What other force would be on the object? Other than gravity? Is that what you couldn't hear? No worries, Ashley. It's all good. It's all good. Is my internet bad? Yeah, let's see.
Yeah,
I'm
it's like
cutting out. Oh, okay. Oh. Okay. All right. Hopefully that's a little bit better. Can you hear me a little bit better now? No? Yeah. So let's just move forward. Maybe it'll get better. I think there was an adjustment that I made that I didn't realize was not there. The question is, so weight is the force of gravity is one force, but there's another force on the ball. Otherwise, if there were not, otherwise it would fall down, right? It's not falling, it's stationary. So
Normal force?
normal force, yeah. The normal force is the normal force. Now, let me draw, now both of those forces are acting on the ball. So I'm going to draw them here on the object. So the weight is mg, it's acting straight down, okay? And there's a normal force, which is the force of the table on the ball, and that's obviously acting straight up. And because it's not moving, accelerating, we can assume that the normal force, basically we can apply the first law like I did earlier. I think I did that earlier. How do we know it's the first law and not the second law? Because there's no acceleration. So when we apply the first law to see the relative value of these forces, the first law says that the net force equals 0, right? So now we put in the forces, N minus mg equals 0, so N equals mg. Clearly those forces are equal in magnitude as dictated by the first law, and they are definitely opposite in direction. So here's my question to you, and anyone can answer. Are these forces pair forces, the normal force and the weight? Antonio.
Are they a pair of forces? Like,
are they pair forces in the context of the third law? Because we define what pair forces are with the third law.
yeah, I think so, because the normal force is equal to whatever force is being exerted on the floor by the ball, right?
Oh, okay, that's true. Yeah. So your statement is because that's true, then you're asserting that these are pair forces. Okay, that's one answer. Anybody else? Ishan, are these pair forces and why?
I'm not sure.
Why not?
Wait, which forces? So it'd be the normal force and the gravitational force?
Yeah, right here on the ball, these two forces. Would those be considered pair forces?
Yes, because they would like because the ball isn't like going anywhere, right? It's in the same place, so they cancel out.
Okay, all right.
Was it your point about like that they're on different objects or something, or is it because they're?
Yes, that's what I'm leading to. That's
Okay.
what I was going to ask. So what we just said here is that action reaction, all forces exist in pairs, and yes, so there are two forces there. So that exists. It could be so that are they action reaction pairs? The law says that they have to be the same magnitude and in opposite directions. Well, that's also true. But the third criteria is that pair forces only act on different objects. Like, for example, when I lean against the wall, I'm putting a force on the wall. So when I diagram that, the force has got to be on the wall or on the bookcase. But then the reaction force is actually on my hand. So that's those on different things, like, and on two different objects, right? When I looked at this object, right, these are definitely pair of forces, and they're acting on different objects because of the one object on the other, right? When you're sitting on your, on your chair, you apply a force on the chair, the chair applies a force back on you. Well, that's not exactly what's going on here. They definitely are equal and opposite, but it's on the same object. So that violates this criteria, second criteria here. So then if these forces are not pair forces, and based on the definition, they don't seem to be, that must mean that there are two other forces somewhere else that are the individual pairs to these forces. Where are they? Where is the pair force for the normal force loose?
They're on one object from what I'm seeing. And
well, let me go ahead.
Well, yeah, like how you're explaining right now for the third pair, like, having the same magnitude, well, the previous steps having the same magnitude in the opposite directions on different pairs. And I see that on the diagram. I see that's on the mass itself and then on the ground.
There you go. Yes, you got around to it, what I was looking for, yeah. So with the law, I apply a force on the wall applies a force on me. So you can use that language for each of these individual forces, and you got to it. The normal force is the force of the table on the ball. So with that language, the pair force of the normal force should be the force of the ball on the table or on the ground, as you said. So the answer I was looking for, the concise answer, is the pair force for the normal force is being applied by the ball on the table. It's here, applied at the surface of contact between the ball and the table. So I'm going to call that N prime. That's where the pair force of the normal force is. And it's being applied, right here. In fact, the normal force, it's not actually being applied there. It's actually being applied here. But the reason we like to draw it at the origin was for the reasons I talked about last week or whenever, when I was talking about how you can move vectors around. And as long as you don't change the direction or the angle, that's valid. So in fact, a more realistic vector picture of this situation is this, where the normal force is actually acting right here, right? That's the normal force of the table on the ball. And then the normal prime is right here, is on the table, maybe at that point. And so that would lead gravity to be acting here. Gravity actually does act at the center of mass of the ball, right? So it's there, that's mg. But, yeah, so that's really more what it looks like, but that's gets kind of messy. And we ultimately, because we're going to evaluate the forces on the ball, we like to draw them from a common point because of vector analysis that we have to vector addition. And ultimately, for problems like this, I'm going to show you that we generally choose the origin step for the problem solving technique to be at the center of mass of that object. So if we can translate all the forces to that point, which we can, as long as we don't change the direction or the angle of the magnitude, that's what we do. So that's why I just intuitively did that. But in fact, that's not actually where the normal force is acting on the ball. It's right there at the place of contact is where it's really acting. Okay. So, good, good, very good, Luz. Good. Emily, question.
Yeah, I have a question. Might be a little bit of an odd question, but I'm wondering, can inertia be a force, a pair force here?
Awesome question. The answer is emphatically and definitely no. Why? Because inertia is not a force. Why? Because inertia is resistance to change in motion. And how do you quantify that? You measure the mass, and mass is a scalar quantity. Now, inertia is related to force, very much so, but it is not force. Just kind of like how you were comparing inertia and velocity, those are apples and oranges. They're related, but they're not the same thing. I would say the same thing about inertia and force. And they are related through these relationships, these concepts we're talking about. Momentum, velocity and inertia, mass, and Newton's second law, force and inertia, or mass. So clearly they're not the same quantity, but they are very much related. So mass is not a force, inertia therefore is not a force because mass is a measure of inertia. Yeah. Does that answer your question?
Yeah, that makes sense. Thank you.
Okay. Now, continuing along with this, we've got the pair force for the normal force. Does anyone want to volunteer? Where is the pair force for the weight? Where is it acting? Anyone? Anybody? Eric, are you there? Want to give it a shot? The question is, if the weight is not the pair force for the normal force, which we have just shown because its pair force is here on the table, where is the pair force for the weight acting on the ball? That's tough. 2 plus 2 was tough until you knew the answer. I think we've had some success with this language of the third law, right? The language is action reaction. You know, I apply a force by leaning on the wall will apply an equal and opposite force on me. I think Luz, we got to that with the normal force. The normal force is the force of the table on the ball. So the ball must be applying an equal and opposite force on the table. See if you can use that language with weight to come up with what the obvious answer is. You don't know? Okay, fair. So someone want to use that language to try to come up with, I don't know, anybody. Sandra, how are you? You want to try it? Use that language, see if you can. And you can state it to the class, like, you know.
I'm a little stuck as well. I don't really know how to go about it.
Okay. Meredith, what about you? You want to try that? Start off with the sentence. Weight is the force of gravity, the force of the earth applied to the ball, and then see if you can finish that out.
I think I'm a little lost too.
Can you formulate a question and let me know what you're lost about? I'm not sure how to help.
How do I, or what am I referring to when I continue, I guess?
Okay. You're referring to, like, it's kind of like you know, when I'm leaning on the wall, I'm applying a force on the wall because I'm leaning on it. So with the language of the third law, that must mean that whatever force I apply to the wall must apply that same force back to me. So where is the pair force for the wall? It's on me. I mean, you know, there's like, so you can take that phrase and apply it to anything to find out what's interacting with what. Does that
So
help at all? Yeah.
a little bit, yeah. Like the resistance the object is feeling from the surface, I suppose.
Well, again, we're talking about weight. So where does weight come from? What causes weight on an object?
Gravity.
And yeah, where does gravity come from?
Not sure.
So here's something that happens. Here's something that you definitely know where gravity comes from, but this is something that happens, right? I don't know if this is like a thing in psychology. I don't know. I only have like a little psychology course, but like there is this pattern that we've all experienced, that you know something, right? But then you expand your mind and you start learning other stuff. And just by doing that, it's kind of like you forget the stuff that you already knew. So that's the thing. I don't know. With me, like, so I kind of feel like something like that is happening. Comedians actually use it a lot, right? Use it a lot because it's almost kind of like, especially when you're learning new things and new things cause you to shift your perspective. And then you kind of get in the mode of thinking like that. And then someone asks you a question and you don't even like, because you're so focused in that perspective, you don't realize it's an obvious question. I think there's this commercial going around now on the online. That's this comedian. I don't know who it is, but it's on YouTube, I think. And I think he's one of these like self-help gurus like Tony Robbins. And he kind of starts off with this. He comes up. He's doing like a TED talk, and he's talking about the brain and memory. And I guess he's one of these people who can help you with your memory. But he gets on. It's pretty good. He gets on. He says, "Hi, my name is so and so, and you know we're here to talk about the brain, whatever." I don't know what he says. And he says, "Oh, but let's do a little experiment. I want to tell you that something he's trying to point out. I forget what the issue is, but he says, you know, like you got your hand and you got a cup, and then he says something like, but then what I want you to do is I want you to take your hand and I want you to put it on your chin, right?" And then he pauses, and then I guess people do that, but then he says, "Okay, people, this is not your chin. Your chin is right here, right?" So magicians and comedians, they use that kind of thing all the time to shift your perspective from something that is completely obvious. But I think it happens naturally a lot of times whenever we're like focusing really hard and we're learning new stuff and we're trying to concentrate, right? So this is not a trick question, but I just want to make you aware of that because you definitely know where gravity comes from, okay? Emily, go for it.
I think it's the force of gravity from Earth, and then what counteracts that is the mass of the ball.
Yeah, it's Earth. Gravity comes from Earth, right? So if you put that phrase in, like with the third law, this is what it looks like. The weight is the force of gravity on the Earth. By the third law, if the gravity is applying a force of the weight of mg, the weight on the ball, then the ball must be applying an equal and opposite force on the Earth. And it is. Way down here at the center of the Earth, this same force that is equal in magnitude to mg is applied to the Earth by the ball. And it is equal and opposite, and it is pointing straight up toward the ball. So that is mg prime. That is, and so you can see it almost looks like this picture, right? Because the distance that the ball is from the center of the Earth is the radius of the Earth, right? It kind of opens up your perspective. So Those are the two pair forces for these forces here on the ball. The normal force N prime, the force of the ball on the table, and mg prime, the gravitational attraction of the ball on the earth. But we're not concerned about, usually we're not concerned about those pair forces because we're really just concerned about looking at the ball and analyzing the ball. We're not really thinking about the earth, at least at this point we're not. But when we start to consider conservation principles, like then we're going to look at objects that are, you know, like gravitational objects of, and we will be able to calculate problems like that. Right? Yeah, so there's not much else I can say about the third law, right? We don't really use it a lot. Well, we do, we use it all the time, but not quantitatively. What I mean by that? From this point on, we're going to look at problems and we're going to apply the law and apply these three laws. Now, I'm going to be asking you as we move forward, when we look at a scenario, which law applies to that? Is it the first law or the second law? That's really what I'll be focusing on, because and asking, and the way that you would determine is by first evaluating the motion. If the motion is constant motion, constant velocity, or no velocity, then it's going to be the first law that applies, and then we will proceed. If the object is accelerating, the answer I'm looking for is the second law. So we'll apply the second law and then proceed with doing the problem. But here's the thing. Whenever I ask you that, you don't have to say the third law, because in every scenario that we consider, the third law will be applying. Why? Because there will be forces on all of these objects, and forces always occur in pairs. So the third law is always going to be there, but it's just not something that we'll be using in a practical way other than just identifying that the force is there and where it's coming from. Does that make sense? I hope it does, but I think I'll illustrate it as we move forward. So if you're looking at a problem and there are forces on it, the third law definitely applies, because those forces have to have pair forces, and that's where the forces are coming from in the first place on the object. And that's basically the extent to which the third law will help you. And there are a couple other exceptions to that when we look at a couple of special kinds of problems. But for the most part, when we start to actually analyze problems and write out equations and develop systems of linear equations associated with the force laws that we're going to solve, it's really coming from the application of the first law and the second law. And the third law is not, it's not there quantitatively, but only there really qualitatively in a sense. Yeah. So, yeah. How do you feel about that? So yeah, that's it. That's all I have to say about that. So that's the introduction of Newton's law. And tomorrow we'll have a long day, a good day, where we get in and start working problems and look at applications of the law. And so, yeah. So, how do you feel? Any questions? Like, what do you think about this class today? Get some feedback. Now that we've gotten into dynamics a bit more. What do you think about it? Yeah, Meredith, are you there? Tommy?
Yeah.
Are you familiar with Newton's laws much prior to, I can't remember, did you say you had a physics class before?
No.
Okay. What about you, Emily Reyes? How are you today?
Hi, I'm doing all right.
Cool. Did you?
Oh, go ahead. So sorry.
I was gonna say, did you say are you a math major? What's your major?
No, physiology.
Physiology. Okay. Yeah. So yeah, talk to me.
And honestly, I feel like the last time I remembered about this was literally in middle school. I think it was 8th grade that my teacher mentioned it, and I remember that he had like several posters kind of outlining the laws, but like very general, not really as specific as now, if that makes sense. But yeah, that was kind of like the introduction, but I never got like a better like foundation for it till like right now.
Okay. Okay, well, good. I'm glad this was helpful. It's just you never know. Like sometimes, so you didn't have physics. You didn't take physics when you got to high school.
No, I took physiology instead.
Yeah, because there's an election. I think you could. I had kind of I could take physics or forget what the other thing was. I don't know. Yeah, most people I think still have a choice. So yeah, I guess if you don't have it in high school, then yeah, no place else that you get it. But this is fundamental stuff, man. This is like definitely for science. So it's basic, and you want to kind of have as strong a foundation and understanding of the basics as possible. So hopefully that this discussion, I spent a lot of, I mean, I don't know, we could have cranked it out and just gone on and done a bunch of problems and stuff. But I think in the long run, I think having discussions like this give a much broader foundation such that when we actually get to quantifying it, it's helpful, I think. So hopefully you'll find that to be the case. Take a look at that. If you find the Cosmos, I think it's on various streaming platforms. I think actually it's on Apple TV Plus, but I think most of them are paid platforms. But if you have that, you might already have it. I think it's worth taking a look at, trying to find some other shows. Yeah. Oh God. Well, I guess that's it for today. I'll go ahead and dismiss class. And yeah. Field any questions you might have if you have any of them.
Oh, quick question. So, how you said before with in terms of WileyPlus and then having the significant figures and like to email you directly or to go through Canvas?
Yeah. So I don't think we were the first week. So all the emails should be through Canvas now for class issue. So
Oh no, I was here the first week, the first day and everything. But it was just
okay.
so like just message you on Canvas, right?
Yeah, email on Canvas. Have you sent an email and I haven't answered it yet or something?
No. I just want to like, yeah, because when you say email on Canvas, I'm thinking like, do I go to your email or just send a message through Canvas?
Is there a difference? Like, so there's a Canvas email and we have an email associated with Canvas. And I think you have like an inbox and you can write emails. So is that email for this class that I'm talking about?
Oh, okay. Yeah, see, that's where I got confused. I think it's like just at least for me, and like people that I've known, we say just message me on Canvas. Like emailing, I'm like thinking like, oh, I have to get your email address, and when it's just like directly through Canvas.
Yeah.
Okay.
It's directly. I mean, there isn't an email address backing that, but I don't think you don't have to know that if you're registered in the class.
Right.
Just that.
Right.
Yeah.
I was the one that got confused, but thank you so much,
Okay.
Professor.
All right, no worries. Yeah. All right. Anything else?
I had a question kind of related to the same thing. Yesterday, when I asked for the extension, you told me to send you an email. I forgot about the having to email you through Canvas, so I emailed you from Gmail instead. And what's it called? So the email on your syllabus, I didn't notice it was like a letter off, and I did and
Oh, is it?
yeah, I sent you an email. I found your email on the campus directory. I sent an email there, but I didn't notice it was off until like very later. And when I got the email saying that like it didn't send correctly, so I sent you through my Outlook email, the school provided email, and I just want to know if I should send you like an email on Canvas now too.
Yeah, I probably haven't. If that email went to my office email, days, but the Canvas email is the one. So basically, in share. So go to yeah. So on the side here, like on the boxes, so that's the inbox right there. And so on that, and it'll put. I think my signal's off or something. But so it's not showing, is it? Okay. So on my somehow my computer signal just went out. I'm still here. But yeah, in the left-hand menu on Canvas, there should be an inbox. And
yeah.
that's the email that I'm talking about.
Okay.
To be able to access, yeah. So it just came back, so if I could pull up real quick.
No, yeah, sorry. I went onto the syllabus and sent an email to there instead. I had forgotten about sending to Canvas.
No worries. So it's this inbox here, and I got about 10 of them I haven't answered yet, so I'm gonna get to them. I'll do that. I know I keep saying that, but I'll get to them today. So that guy, and so somehow you can just, you can come here and you can pull up a new message, and from you, when you do that, it just comes directly to my inbox.
Okay.
And
thank you.
that's the one I'm referring to. Okay, cool.
All right. Thank you, Professor.
All right, thank you. Yeah. All right. Anything else?
Professor, I was hoping that you could help me solve a question from the homework that I'm having trouble on, if possible.
Absolutely.
Okay. I can share my screen like I did yesterday.
Yeah. Go ahead. Are you trying to share it right now? Hello? Yeah.
Sorry, my computer froze, but here it is. You can see my screen, right?
Yeah.
So it's this question. I tried solving it and I didn't get the problem correct. So I was hoping maybe you could tell me if I'm doing anything incorrect.
Okay. The picture in slow pitch softball game, a slow pitch softball game, realizes or releases the ball at a point 3.02 feet above the ground level. The stroboscopic plot of the position of the ball is shown in the figure below, I guess. That's what it should mean. Where the readings are 0.255 seconds apart and the ball is released at t equals 0 seconds. A, what is the initial speed of the ball? What is the speed of the ball at the instant it reaches the maximum height above the ground level? And what is the maximum height? Okay. So this is one of those situations where we need information from the graph to solve it. My first intuition, so this is accelerated motion, it's free fall, it's basically parabolic motion, right? So the most powerful equation, so let's just go through and do it based on the problem solving technique. You can see the board for me, right?
Yes, I can see it.
Okay. So it's parabolic motion, and we have the initial position, y naught is equal to 3.02, was it meters? Yeah. And then I guess we do know the total time because we know the time between each increment. So the total time is, I guess, 1, 2, 3, 4, 5, 2.55 times 5, and then we have the increments of each.
Professor, it's feet, not meters for why not.
Oh, okay, feet. All right, thank you. Now, what also is confusing me a little bit, it says that, oh, this is y of x. Okay, that's the x-axis. The x-axis is just x is not, okay, yeah, I was thinking it was time. So that's good. That actually gives me a hint. The graph that they're giving, so that's important. So the delta t for each time period is equal to 0.255 seconds. And I guess we know the total distance, the total x naught is actually 0, and is 0, but x final is actually 40 meters from the graph. And y final is 0. Y final is 0. Well, actually it's not. Y final is whatever it is there. I guess you could, oh, it's a perfect parabola. That's one thing we can see. It's a perfect parabola right there. That gives a lot of information. I don't know what time period that is, but it's definitely, basically the y position is the same as whatever the final y position is. You can see that by just tracing horizontally across the graph. So I would have to read the graph to see and do and we don't need to do that. I don't think we're gonna need to have that information to have the specific value of y. Yeah?
Oh, sorry, I just had a thought, but let me figure it out.
But what we can definitely say is that delta y is equal to 0. And that's important because of our equations of motion. Now, and also the other thing is that the graph is showing x versus y, not y versus x, not y versus t. Okay, that's steps 1 through 3. We could graph it, right? Could draw it out. I could do that. But it's kind of a graph and it's going to look kind of like the parabolic path like that. Basically, they've given it to us right there. So I'm just going to leave that. Now, step 5, what applies? Parabolic motion, that's the concept. Write down the generalized equations associated with parabolic motion. Let's do it. So we've got velocity, x equals x naught plus v, x naught times t. Then we have vy equals vy naught minus gt. Then we have y equals y naught plus, and actually this is a plus because in the y direction, you can see that he throws it up, right? It's a parabolic path. So, I don't think we're going to need that, but just to note that if you take the initial y velocity v naught, and I think we talked about this yesterday, that's what's happening right there at time t equals 0. So the y component, the x component is positive, which I showed here, but the y component is also in the positive direction, which is this second term here. So that's a plus sign because of the way that it's being thrown at a positive angle relative to the horizontal initially. So that's a positive vy naught t. I don't know the value, but all of that I still know from how it's being thrown. All that's implicit information, minus 1/2 g t squared. Vy squared equals vy naught squared minus 2g delta y. 5 delta y equals 1/2 vy naught plus vy times t. Continuing on, the range equation, the y versus x equation, y of x is equal to y naught plus tangent theta naught delta x minus g over 2 V naught squared cosine squared theta naught times delta x squared. And this is the thing I was pointing out. Delta y equals 0, which means we can actually take the easier version of this. The range equation also applies in this case, which is that the range, delta x is equal to the range equals, what is it? V naught squared sine 2 theta naught divided by g. Now that in conjunction with the trigonometry stuff, all the stuff that we need now has got to be on the page. Okay? So now let's go for what they're asking for. Let's go for the juggler. What is the initial speed of the ball? Well, we can, I didn't go through the zeros, and let's just go for it. So let's find all the places where the initial speed is. Now, remember, the most powerful equation is this guy. But this is a special case of that. So the first thing I'm going to do is go here. That's the most, it's several places the initial speed, but actually only 2 places, because here, that's the initial speed along the y direction. That's a component of the initial speed. The only 2 equations where the total initial speed exists is in equation 6 and 7, there and there. If you understand, which you should because we derived it, that this guy is a special case of this, then this thing is what we should go for. Let's look at that. I think we're going to have all the information we need from that, or at least be able to determine. We might be. So that's definitely an unknown. That's what I'm looking for. So is there anything else in there that is known? If so, it's a plug and chug that I can garner from the graph. Well, I do know delta x, that's 40, right? Because I can look along the graph and see that it translates 40 meters. I definitely know g. So the only thing I don't know is that initial angle. All right, so I'm embedded one level in the product. Is there a way that I can figure out the initial angle of the that is thrown at? And let's see. It's something that, what is the initial speed? The pitcher in a slow pitch softball releases the ball at a point 3.02 feet above ground. A stroboscopic plot of the position of the ball is shown in the figure below, where the reading is 0. What is the initial speed of the ball? What is the speed of the ball against the altitude? Okay. Well, it doesn't look like I will be able to get the initial angle from any information shown. So if I can get the angle, though, that's going to be a way of moving through, maybe some other way. But it's a good try, but we're not going to be able to get that from there. And I think these other equations are the same, right? Because this is just a special case of this guy, that you would need to know the initial angle in order to use either 6 or 7 to determine the velocity from either one of those 2 equations. So let's go ahead and follow through with the technique. So this guy is, so here that's known, and delta x is known, and also both of these. Well, you don't know them, but you know the delta y, and that just led back to this thing, right? So we'll just put that in like that delta y equals that. So I'll put the known values in green and the unknown in blue, right? So basically delta theta. Again, if I get delta theta, then I can use that. I can't now, though. All right. So let's the only other options, I guess, is to go to some of the other equations to see if we can find that. Now, with those are component equations, so we got to be a little bit careful. Okay, I have an idea. We can determine, I can see how we can determine, so I'm kind of focused on velocity right now, right? So one way to get the velocity is another way to get the velocity. So we got to come up with some algebra. We know that at any point, like here, this initial velocity is equal to the square of from the geometric equation. I didn't write them down, but it's equal to the square root of Vx naught squared plus Vy naught squared, the square root of that. So if I can get V naught, Vx naught, and Vy naught, I can put it into this Pythagorean theorem based on this geometric relation, and that will give me V naught. And I can see right now that we have enough information to do that. Let me show you how. Vx naught comes from this equation, because if you go through and look at the knowns and unknowns, here we have, this is going to be x minus x naught, right? X minus x naught equals Vx naught times t. Well, we can figure, we definitely know delta x, that's 40, but we can also figure out t. It's what I almost did initially, because we know that we've got 5 data points and there's 2.55 seconds between each 5. So the total time is 0.255 times 5. So we can definitely get Vx naught. You agree? And we'll do it in a second, but just let's just keep do you agree with that, with what I just said, Emily?
So far I was solving it the exact same way.
Okay. Now we can get Vy naught from this guy, but doing half the distance. Well, actually total. That's one very interesting thing about this equation. We'd have to use the quadratic equation. No, we wouldn't actually. We wouldn't, because, oh yeah, we would. Because we can, actually we could do that, but there's an easy way to get it, actually, based on the information of the graph. So we could get, at any point, we could look at, so we could do the total distance. So, the time that it takes for the ball to go up and come back down, we could use this equation to determine that, but we'd have to solve the well, we don't know, because delta y is 0. So we could actually get it pretty easy there. Again, we've already calculated the total time. It's 5 times 2.255. But then from this equation, let me just come over and write it again, write it down. So I'm going to call this equation 8. But from this, we could write equation 9. The delta y is 0 for the total distance. So we could say that delta y equals Vy naught t minus 1/2 g t squared. So that if it's y total or t total, then, and this guy is going to be 0 for that. So we could write that equation as 0 equals Vy naught t total. I'm going to put that as if I'd put that time in, minus 1/2 g t total squared. So one of the t's cancels, and what I have is Vy naught equals, when I take this over, the minus sign will cancel that one. So Vy naught is just going to be equal to minus 1/2 g t total, because the square will also go out because one of them cancels. So I can get, so positive, I can get Vy from that equation, where t is the total time. And once I have those two, I can put both of those in here to get the total velocity. Do you agree with that?
Yeah, I agree.
Okay. Now we'll do that in a minute to test the answers because maybe you did that and got the right answer and they marked it wrong for some sig dig reason. I don't know. But that seems pretty solid to me. So what else are they asking? What is the initial speed of, so what is the speed of the ball at the instant it reaches its maximum height above the ground? We already have the answer. It's this speed for the reasons we talked about yesterday. Because the speed in the x direction is constant because there is no acceleration in the x direction. And if you go back and look at where I went through that detailed picture that looked kind of like this diagram they had, we went to the top and I told you that as the ball goes up, the y velocity is decreasing. And it's zero, the y velocity is zero at the maximum height. Okay, can you hear me again?
Yes.
Somehow I'm not. Is that better? Say something, please.
Yeah,
Make
I
a comment.
can hear you.
Okay, there you go. All right. Yes, so once you get to the maximum height, the y velocity is zero. And so the total velocity of the object is going to be just the velocity in the x direction, which is constant at every point in the motion, which would be the value that we would have found from this equation. Does that make sense?
Yes, it does.
Okay, so that takes care of that. And part B or part C, what is the maximum height? Well, we could get that a couple ways. Now that we have the, we could go, probably the easiest way is equation 4 here. Because I know from the graph, I can determine, well, can you? Yeah, you can just read it from the, that's kind of simple. You can just read it from the graph. Couldn't you? Yeah, because it starts at 3.0, like you can just read that directly from the graph. Is there some way that you can blow this graph up? Like you don't even have to calculate it.
No, it's just embedded.
Okay, but you could, there you go. Yeah, so look, it starts at 3.2, whatever it said, and then it goes up. Like each increment is going to be, I guess you'd have to figure out what the increment is, but you can definitely figure that out. You can see, so is that the way they want you to do it? Because if it's at 3 points, what did it say, 3.02 feet? Each of those increments is got to be, so 5, 1, 2, 3, 4, 5. So 5 into each of those increments is 0.25 feet, right? Maybe they don't want you to, I don't know, because each increment is each increment is 1, 2, 3, 4, 5. Each increment is 0.5 feet. No, each increment is 1 foot. 1, 2, 3, 4, 5, 6, 7, 8, 9. So that would be 9 feet just based on what it looks like from that graph, the maximum height, but maybe that's not what they want you to do. But let's go ahead and calculate it because I don't know. Maybe it's not, because it says the thing is at 3.02 feet and 1, 2, 3. And you can see right there, like it's not that, it looks from the dot, it looks like it's just on 3 feet. So that implies to me that they don't want us to get the answer from just reading it off the graph. But that's okay. So that's fine. We can do that. Go ahead.
I got my time by reading off the graph. It's like what you said about the perfect parabola. I think
not the height necessarily, because it doesn't, I think that's the point. It doesn't show the very top point, the very middle point where it's at 20 feet, x equals 20 feet. But I did get a time with this graph. I multiplied. Did you do that? I wasn't, I was kind of like focused on like my own little paper. I wasn't even,
Yeah, I said it, but I didn't do it. But technically speaking, we aren't getting it from the graph because they give us the value.
Sweet.
You know what I'm saying? So
0.6375.
You mean the total time to go across or what?
Oh, the total time for it to reach the middle. So where the height is.
Oh, yeah, I don't know. I have to calculate it, but I can, what it's going to be is the total time divided by 2 because of symmetry. So the total time is 0.255. So you have 5 data points. So 1, 2, 3, 4, 5. Yeah. So the total time is going to be, let's go ahead and calculate it now. So 0.255 times 5 is 1.275. So the time that it takes to get to the maximum height is going to be half that. So that's going to be, yeah, well, I think it's what you said, 0.6375.
Yeah.
Yeah. Yeah. But that's not, technically, it's not from the graph. I mean, it is, but it's not read directly from the, it's just because they told us. So I'm kind of using that quantitative value and qualitatively what I know about parabolic motion, which is, like you said, you know, it's symmetric. That's got to be the case, but I'm not actually reading that number from the graph. That's not what's happening. So, but whatever. That's just maybe rhetoric, just syntax or whatever. Anyway, so yeah, so we agreed that the time to half is 0.6375. So we could use a couple. Now that we know that, we could what is it asking? What is the maximum? Yeah, what is the maximum height? So we could use, yeah, well, yeah, it looks like we're going to have to use a calculated value to get that, right? Because there's several equations we could do there, but now that we know the time, but all of the ones that involve using the time also involve using the initial velocity in the y direction. So that's the best way to go. So it's either equation 2, actually we could do equation 5 or equation 3, either one. Because so by now we know Vy naught, right? So if we know that time, we could use this guy. We know that the final velocity, oh no, we're looking for height, so I'm sorry. So we could use this guy. The initial height is 3.02, so that would be known. The initial velocity in the y direction is this thing that we calculated here, and the total time is going to be the 0.6375. So that's one we use. We could also use this equation here without calculating the time. So that might be a nice one to use, because we know when it gets to its maximum height, the final velocity is 0. The initial velocity, again, we just calculated. And this is actually y minus y naught. Y minus y naught. So y naught is the 3.02, which we know. So the only unknown now in this equation, green in the so the only unknown in this equation would be y, which we could solve for. So that's known. And so yeah, and yeah, you could do 5 as well, but that's just more than you need to do, because you have to, in either one of these, we either use the unknown, you either use time here or use the velocity. Well, here I guess you have to use both time and the time and the initial velocity. In this case, we only would need to use the initial velocity. And in this case, we would have to use the time and the initial velocity again. So y minus y naught. Yeah. All right, so that's how to do it. Let's go ahead and calculate the numbers and see if we have any issues with other issues with the WileyPlus. But in terms of the physics, does that seem reasonable? Does that answer your question, Emily? And I mean, does that feel like that? Did you do all that and get those? Is that what you did, or is there something that you didn't do?
I did. I can't remember exactly which steps I did differently, but I did do some steps differently. But obviously, there's multiple ways to solve problems. But
Yeah.
yeah, it makes sense in terms of the equations, and I think it does that we have to find the velocity first before we can solve the maximum height. So yeah, it makes sense.
All right, so let's go ahead and put in the numbers and see if we get the same numbers. So here, so let me go ahead and get this guy first, because that's something we can check directly with part B. So that's basically going to be 40 meters divided by the total time, which was 1.2 something. Yeah, so store. So I'm going to go ahead and put this up. The total time is T total is 1.275 seconds. Store that in my zero register. So that means that my velocity in the x direction should be equal to 31.37. I see that's what you put down, didn't you? No, you put 31.4. Yeah, 31.4. So I got the same thing for what you put for part B, 31.4 in terms of significant digits, 3 significant digits. Yeah. So it marks you wrong for 31.4?
Yeah, for all of them.
Yeah, I don't agree with that. We can look up the answer. In fact, that might be what we should do, right? Just so it's safe as having the question. You got the same thing?
I got the same thing, and I did it well, I'm sure the math is the same, but I did it a different way, the way I always did in high school.
Okay. Tell me, how was that? I'm just curious.
Oh, it's kind of like, I think it's mainly the symbols that are different, but I kind of like, I split it into, well, I don't know. I think it's the same thing, because you're using Y, you denote if it's like a Y or if it's like an X, right? For your velocities. Yeah. Like,
yeah.
I just kind of keep them apart. It's the same thing. I do DVI-AT, DVI-VF.
Cool. Yeah, I was going to say, because since there's only, for parabolic motion, there's literally only one equation that defines the horizontal direction. So there are a couple ways to get other stuff, but for that thing, there's only one way. There's only that one equation. So I was just curious. But good. So now you see that we're on the same page. That's awesome. Yeah. So you know what? Why don't we just let me pull up the solution and just text it, because I have a feeling that these are all right. If you got that right, then I see no. Well, actually,
I did get 37.4747 for A, and then I got it was something closer to 31.36 something for B, and then for C, I got 9.55343.
You know what? Just to check significant digits, let me go ahead, because I definitely got the 31.4 for part B, and I didn't round anything. So I would say that was the closest the correct significance. So let me just check the others just so we can check that as well. And let me store this in my register 1, store 1.
I will say that I think in terms of the significant digits, I think we may have gotten different answers, because like for this problem, everything's in feet. So you have to convert feet to meters, which is around 32. And you can either use 32, but I use like as many significant digits as possible. So it was
Mhm.
like a really long number. So that might be like why we might be getting slightly different answers because they're pretty close, but I'm not entirely sure.
Oh, you mean that when you converted G from 9.1 to 32? Because why do you have to convert?
Because it's the problem is in feet.
Yeah, but why do you have to convert anything?
Feet to meters because of the acceleration.
Yes, for the gravity.
Okay, yeah, but that 32 feet per second squared exactly is generally what. Well, maybe if you took the 9.81 and converted it to that. I see. Yeah.
I use
What
like
they
281 conversion.
say again?
I use like 3.281 for my conversions.
Oh, that might have done it because they probably use 32.
Maybe, yeah.
Just 32.2. Because in high school, right? Like if you look it up, I think it's going to say 32 exactly. Right? Because if you use 9.81, that's a truncated value. We just decided to use that in class because we're doing it with 3 significant digits. And so it rounds to that. But that's not actually the number, right? It's 3.81 and some other change. And that's where, when you put all those numbers out, I think you're going to get close to 32.0. So that's a good point. That's a good point. I think at this point, I think we should, let me just pull up the number. And I think this is a matter of significant digits. So you don't have this, you don't give the solution there, right? You can't access the solution at this point, right?
No.
Okay, so let me access it. So you back out and let me pull up my screen and pull up that problem. And I'll pull it up for you. And what number is it?
Number 31, I believe.
Okay.
Yes, 31.
From which homework assignment?
Homework 2.
Okay. Which number?
31.
Okay, this is it. They used 32.2. What did you say you used?
32 and like I don't remember all the numbers, but it was a bunch of numbers after the decimal.
And what about you, Antonio?
I didn't convert the acceleration. I actually converted the whenever I would use
I see.
distances.
I got you. Well, it's looking like it's giving the answers we got, right? So A was 30, so that is 37.4. So that's what you put it and marked it wrong, right? Oh, you put 37.2. Okay.
I put 37.2 and then 31.4 for the second one.
Oh man, it's crazy. I'm so sorry about it. I don't know why this thing does this. I don't know how to stop it. So you got that right. And then what's this one? Yeah, 9.6. You put 9.3. Yeah. Yeah, all right. And that, I think you said you got 9.6, right, Antonio?
I got 9.56.
9 point, so that's rounds to 9. Okay. All right. Well, you got them right. So I might, so like when I go back to this, I probably would get like 0.9 of a point. That's kind of what I do for the whole thing. So you only have 0.1 of a problem or 1/10 of a point off as opposed to 9 tenths of a point off. And that generally suffices for that. Yeah. But good.
Sir. Okay.
Good. So you're definitely doing the right thing, and that's awesome. It's awesome. Yeah.
Can I also ask about number 8? I don't know if it's a rounding error again, but number 8 is just A that I got, or sorry, it was not number 8. It was number 21.
Let's just check the answer first to see if we need to. Second one is right, 50 when. For the first thing, they got 116. Is that degrees? Okay, so there's. I have to look at. So let's take a look. I don't know. I haven't even read the problem. So it looks like they're saying that one's wrong. What about you, Antonio? Do you remember that problem? Did you get it?
No, but doesn't 56 and 116 almost add up to 180? So maybe it's like maybe it's like one of them things where it's like you did it like whatchamacallit.
Yeah, you're right. Good catch.
It adds up to 172. I'm not sure actually.
It still could be a rounding error. Let's see. So it looks like they're talking about the angle with respect to the vertical. So is your angle with respect to the vertical or with respect to the
axes?
The horizontal, yeah. Do you remember when you did the problem? That's actually a good point.
I'm not entirely sure, but I might have made that small error. That's possible.
240. No, go ahead.
Sorry, I read the wrong thing. It was the angle was 25. That doesn't add up to 180. It adds up to 141.
Well, I think we did something like this yesterday, but the 240 is this. It's not the one we did yesterday. So 240 Wide River. The speed is 1 meter per second through a jungle and toward east. An explorer wishes to leave a small clearing on the south bank and cross the river in a powerboat that moves at a constant speed of 4.7 meters per second with respect to the water. There's a clearing on the north bank 60 meters upstream from the point directly opposite the clearing on the south bank. At what angle, measured relative to the direction of the flow of the river, must the boat be pointed in order to travel in a straight line and land in the clearing on the north bank? Okay. Okay, so in the north, yeah. So 60 over, so tangent, set up like that, tangent of 60 over 240. So that's not going to be the angle they're asking for, but I just want to see if that's what you did. That could be an easy kind of mistake, 240 divided. And then yeah, we have to go through and do the problem. Like I could do it here. You can see me, right? We can try to work this out right here to get that part, the angle.
You.
Yeah. So the way I'm viewing this is we got this guy, we got this guy. It's going to start from here. This distance is 240 meters. And yes.
So if we end up working it out and we find the solution to be the exact same as what they give us, then does that mean we get full credit for the problem?
I still take something off for significant digits.
Okay.
Usually, because that's the issue. You did get it wasn't the right significant digits. But like it's just a tenth of a point. So you get 9/10, out of 1. So that still is an A, and it doesn't really affect your grade much. That's what I've been doing. You think that's not fair or what?
No. I was just wondering if I thought we don't get it changed. That's what I was thinking.
Oh no, I change it. Like whenever you send me the email, I just haven't gotten to it yet. If you already sent an email, I haven't changed it yet. No, anytime this happens, you send me an email with the numbers of the ones you want me to look at, and I go through and do basically what I'm doing with you right now. And if it were like when you send me if you haven't already, go ahead and send me the email for this problem. When you send it to me, I'm gonna go look at it, and then I want to change the grade. I can change it from my end, and it will change your grade.
I got it. Thank you.
Yeah. So for the ones I thought you understood that. So for the ones we've already looked at the past couple of days, if you haven't sent me an email, send me the email. I just haven't addressed all the emails yet, so I haven't gotten to it. But I will, and I will change it, and it will change your grade.
Okay. So.
Okay. Yeah. Yeah. All right. So the river is going at 1 meter per second. So I'm going to assume my axis is here. That's the point where he's moving from. So this is X and this is Y. And this vector represents the flow of the river at 1 meter per second. We'll say to the right, I guess we call this north, south, east. So this is V river is equal to 1.0 meters per second. And we want to end up over here someplace 60 meters down river. So that's on the north bank. So that's here. So this distance here is 60 meters. So basically, we're going to have our velocity is going to have to be at some angle like this. And I think that's probably the picture that they're showing, because that's kind of what, like, I'm actually traveling, along a line here, but I can see intuitively, I can see that I've got to be pointing at some angle. My velocity has to be a constant velocity that's pointing at some angle like that, so that it compensates, and I'm moving along like this. All right, so what we're looking for is this angle right here. Agreed?
Yes.
Now,
So far, so good.
Okay. So I don't know what that velocity, or it gives me the velocity though, does it? Of the boat. Yeah, so I know that. I'm gonna call that V naught. So V naught is equal to 4.70 meters per second, or 4. Do it in black so you can see it. V naught is equal to 4.7 meters per second. Now, I'm going to have two components, right? Because I got to add vectorially. That's how I'm going to get the answers. And I got to have all the components, all the vectors resolved along the component directions. So here, this is going to be V
V naught, Vy naught, and this is Vx naught, which is along the negative direction. And so my equations, the motion that would define this motion, I guess, is that V, Vy, Vx naught. So actually, so yeah, we got to have, first of all, you have the resultant. I guess really we're only concerned with the y, because this is the only thing that's going to get us across. Is that true? Let me think about this. I'm trying to throw in a blank. Well, what we know is this, is that Vy naught, because that's, we want to know angle, and Vy naught is going to be equal to V naught times the sine of theta naught. And the theta naught is the thing we don't know. And over here, and also the Vx naught, Vy, and Vx naught is equal to V naught times the, oh no, oops, that's opposite. The way I've set up the problem, Vy naught is cosine of that angle. Vy naught is V naught cosine of theta naught, right? Because theta naught is that angle, which if I put it in the context of these velocities, it's right here. That's theta naught. So this y component is the cosine, and the x component is the sine. Because and that makes sense, because usually it's the opposite, the other way around, but we usually use the angle with respect to the horizontal. That's the thing Antonio was talking about, but from the point of view of velocity. This is the angle, the vertical angle. So Vx naught is equal to V naught sine theta naught, okay? We're looking for theta naught, but Vy naught and Vx naught are also unknown. It doesn't tell us that. Okay, fine. And I don't think we know the time either, do we? That it takes him to do all that. No, it doesn't give us that. So we got to go to the equations of motion to get the other equations. Because that's right there, that's three unknowns, and that's only two equations. So we can't just use geometry or whatever. So what are the equations of motion? Well, it's we have constant motion in both cases. The equation that defines how fast he gets across the river is going to be, I'll call it constant motion in the y direction, and that's going to be y, and well, actually delta y, right, which is the 240. So delta y is equal to Vy naught times t. Call this equation 3. And we know what Vy naught is. We can substitute this in. So delta y is going to be equal to Vy naught, or say V naught times the cosine of theta naught times t. And that equation just has two unknowns. So I can feel it, we're getting warm of what the ultimate solution is. That's an unknown and that's an unknown. Okay, we need another equation. We can get it from the translation. That's constant motion as well. And we have that distance. So in the x direction is also constant motion. And that equation is going to be delta x, which we know, that's the 60, as I said, is equal to Vx naught times t, okay? But we have Vx naught in terms of V naught. So delta x is equal to V naught sine theta naught times t. And that's it. That's the solution. We combine equations 4 and 6. See it? There's two equations, two unknowns. The two unknowns are also here in this equation. And so you can substitute one and the other for t, or you could just divide one by the other. I think that's what I'm going to do. It's easy. If I divide, well, actually I divide equation 6 by equation 5 so I can get tangent as opposed to cotangent. So 6 divided by 5 is going to be delta x equals V naught sine theta naught over t divided by
delta y equals V naught cosine theta naught divided by T. So the T cancels, obviously. The V naught cancels. And I'm left with this equation that delta x over delta y equals tangent theta naught. So the final solution, taking inverse tangent, is that the tangent, is that theta naught equals the inverse tangent of delta x over delta y. So that's my solution. So let's see what the answer is. So theta naught is inverse tangent. Delta x is so 60 over 40. That's gonna be 1/4. No, yeah, that's 1/4, right? Because 60 goes 1 and 60 goes in 240 4 times. So inverse tangent of 1/4. So what is that? 0.25 inverse tangent. I get 13.4 degrees, 13.49 degrees. What did they get? I think that's what they got. We saw that somewhere. Oh, that might be the, is that what, I thought I saw that somewhere. It's not what they're saying here. Usually the angle between the normal. Delta x 60 over 40, 240. Yeah, it's 0.25. And inverse tangent of 1/4. It's got something to do. Um, intuition here, so it's going. I'm missing. Oh, I did. I am so sorry. I missed something. I screwed up. I didn't take into consideration the flow of the river. This is the answer if the river is not flowing at all. There's a term in here that I missed the 1.0 meters per second. It's here. I missed that. Or here. The x distance, it travels shorter than that because it's the velocity of the boat. Actually, yeah, it's the velocity of the river minus the velocity of the boat times time. Ugh, I'm sorry, I'm going too fast. That's definitely a problem. So let me just put that back in and do it again and start from there. So let me. Is still there, everybody?
I'm still here, yeah.
Yeah, you see that? That's definitely
Yeah.
a problem. I don't know
Yeah,
if
that
I'm.
always happens to me too. It's like one number you forget and you have to start all over.
So doing that qualitatively, it would be 1.0 meters per second minus, because I don't know what that is, minus Vx naught times T. So delta X then is equal to 1.0, I'm just leave that because we know it's velocity, minus V naught sine theta naught times T. So that's going to end up being delta X. And what it would be is like, well, I just do this step. So minus 1.0. Oh, is that T not going to cancel out now? Well, no, I'll just leave it like that. Just leave it. Okay. So I still have two equations and two unknowns, but that's going to give me that's going to lead to a quadratic equation. It won't be as simple as what I just did. It's going to lead to a quadratic. But let's go ahead and do it. So basically, I could take this T and substitute it into here. I think it's going to lead to a quadratic. Or maybe not, I don't know. But I think that's it. You know, that's two equations, two unknowns, and we have to solve them. So this is an unknown and this is an unknown. So I could take this T and substitute into this one. That's what I'm going to do. So delta Y divided by V naught cosine theta naught equals T. So putting 7 into 6, that's going to be delta X equals 1 minus V naught sine theta naught times T, which is delta Y, V naught cosine theta naught. And so and so now it's just algebra. I'm going to simplify this guy in here, multiply through. So I'm going to have delta X. Is that the way to go? I think so, because I got to get those things together. So delta X equals basically this. Oh, wow. Is that like a transcendental equation or something? Because I'm going to have delta Y over cosine of theta minus, so times V naught, minus, V naught cancels here, and this would be, well, you know what, I could, yeah, I could just take the delta Y over. I'm gonna go ahead and do that. So, this will be delta X over delta Y. And that's going to be equal to, when I multiply through, 1 over V naught cosine of theta naught minus V naught cancels, and that would just be tangent. There you go. That can't be solved. That's what they call a transcendental equation. It can be solved numerically, but not, I don't think analytically that I know of. Hmm. Yeah, I don't see. Let me look through that again. So yeah, so here it's definitely got to be pointed in that direction to hit the flow there. If it's pointed there, it's going to miss, right? And right, if the river is not flowing, it goes straight across. If the river is flowing, it's going to hit like that. If the river is flowing, that would take it here. Um, 240 meter wide river has a uniform flow from toward the east. Okay. An explorer wishes to leave a small clearing on the south bank and cross the river in a powerboat that moves at a constant speed of 4.7 meters per second with respect to the water. There is a clearing on the north bank 60 meters upstream from the point directly opposite the clearing on the south bank. What? You know what? I see why I got a transcendental equation. I've set the problem up wrong. That point is downstream. That point is downstream. So I think I've created something that's it's going to give something that's physically not what is happening and what can happen. This is definitely not right. Upstream means
upstream from the upstream is implying the direction from which the river is flowing. So that point where he touches has got to be on the other side, on the west side of the point from where he started, because that's upstream. So he said 60 meters upstream. So the point has got to be over here. It's got to be over here. Let me take this out. So this is going to be the 240. Here. 240. This has got to be the 60. And I think that's going to affect the relative directions of the vectors in some way, because this is actually the physical path that he's taking here. So guess it would have to even be more an extreme angle than what I had. My inclination is still to, right? Because yeah, it's got to even be like more extreme relative to the vertical. Okay. So I'm still going to have the same picture with velocity, but it does change something. Right. So and that angle here is measured relative to, still measured relative to, let me do what it is. All right. So yeah. Why not? Next. You know, second. These things are still true if I'm defining this guy as the angle relative to the vertical. I think I can still do. So moving like that. Still. Here. He says it goes upstream.
Okay, upstream means it's got to be west of the point across. So if the point is across here and it's 6 meters upstream, this is downstream toward the, so this has got to be upstream. Okay. Yeah. So I'm still gonna make this the angle. That's still theta. So these would still be true. Okay. Now the equations of motion. Delta x. Wow. Although it makes the delta x negative. Yeah. In the negative direction. Delta x is negative, then that just flips this around, which makes that Vx naught is going to be greater than 1 meter per second. Yeah, let's do that again, but I don't really see what's going to change up in the result. Very much this I have. So I'll flip it around, sure. So Vx naught minus the 1 meter. And delta x is equal to V naught sine n naught minus 1 minus t. You know what? I'm gonna go for B first. Maybe we don't have. Maybe I could do it. Maybe no. So we can get that from this guy. Just see if that time is. We can get that from equation 3. So for the time should be equal to t is equal to delta y over v naught cosine. Oh, but I don't. Oh, because I need the angle to do that. But maybe that gives me another equation. I can v naught cosine theta naught. Well, that's kind of what I did, isn't it? Yeah. So then you take that. So once we have theta naught, that's how you get the time. But to get theta naught, I would have to substitute that. Actually, yeah, because we can't eliminate theta, can't? No, because if you'd have to do one is sine and one is cosine. Yeah, I don't know. So putting t into this thing, I'm going to get what looks to me like a numeric. You can only do it numerically. I don't know, unless there's some method of solving it that I can't remember. But I'm just going to do this and we'll look at the solution. So that's 7 and then 8. So delta x equals v naught sine theta naught minus 1 times t, but t is delta y over v naught cosine theta naught. Yeah, so I'm going to end up with same thing I had before. So delta x over delta y, just a sign change, though, which is going to be equal to tangent theta naught minus 1 over v naught times the cosine of theta. And right now, I'm not thinking of, could you do an expansion, Taylor series expansion, and take like the first couple of terms? I don't know. I don't know how to solve that. I think you'd have to use numerical methods. Or, wait a minute. Yeah. Yeah. Yeah, it's not this, it doesn't have anything to do with the angle of this thing. That's something else. This angle is the angle that's pointed where to get there. And that's information I didn't use. I don't know if I could, that would help me in any way. Is there any way that I could use that to get the time? Like, huh, wait a minute. Wait a minute. Oh man. Yeah. Oh wow. I think I see something here. This is information we didn't use, which is always, so this angle, I'm going to call it beta. And it's the angle, the geometric angle of the line that they actually travel. There, I know that angle because I can figure it out from this thing. It's the angle that I figured out, but it's the 13 degrees. Because in that, I could write this distance in terms of that. And I could also use that to give them, that would give me that's the same distance as yeah, I mean, I know that distance, so I think I could use that distance to get the time across. So it's basically a different equation to get the time as opposed to one that's connected to this because it's a different angle. But it's the same time to get across as this time. And so then I might be able to use that time to get this. Let's do that. That might do it because, okay, so tangent of beta is equal to opposite side over adjacent. So that's the 240 over, so beta is 60 over 240. That's 60 over 240, which leads to the 13 degrees. So beta is going to be equal to the 13 point, so 1/4, right? Inverse tangent of 1/4. 0.25 inverse tangent. 14 degrees actually, 14.0. That's a whole number too, so that's promising. Let me, sometimes they set them up like that. So store 0. So that's going to be 14.0. So approximately 14.0 degrees. Now, what I could say is that this distance, the 240 equals, is that going to help me in any way? 240 equals, well, I know that. That's the distance I take to go across. So that is, yeah, so
that's not gonna help me. Somehow I gotta, that time to go across is, can I associate the time to get across with that? I know the distance, I know the velocity. Distance equals velocity. Oh, because it's not the total velocity. But what about this distance here? The Pythagorean theorem. Oh, yes. Yeah, I know that distance. That's the thing. That distance I'm going to call d. There you go. But that's going to be the total. Is that the same time? Yeah, it's the same time. The same time as I do this is the same time as I do this, is the same time as I do that. Yes. So d is equal to 60 squared plus 240 squared. That's it. This is it. Wow, this was not such an easy problem. Not for me anyway. So 60 squared 240 squared plus square root 247/38. So store that in 0. 247, 38, and this is register 0. Now, yes, so now I can use the constant motion for this thing. That diagonal d is going to be equal to the total velocity, not the component, because they give us that. The total velocity times the time. That's it. So that's an easier equation because it doesn't have a sine or cosine in it. So that's the t that I can substitute into either one of them. And that's it. That's 3 equations and 3 unknowns. The 3 equations are 1, 2, and a geometric equation, 3. So I can solve for either one. That's it. But yeah. Or we could just get the back, because they're asking for the time anyway. I think they asked for the time. So we can just get the time here and then substitute the number in so we don't have to solve it, algebraically. So d is divided by v naught is equal to that t. So that's going to be 240 divided by the 4.7, right? 4.7. So yeah, the 247. 247.38 meters divided by 4.7. So that time is equal to 52.63. And I think that's what they got. 52.63 seconds. I'm going to store that in register 1. Store 1. And let's see, is that the time we got? Yeah, 56.8. You know what? I did the same mistake again. I forgot to take into consideration the velocity of is that true? No. I don't know if I agree with that. Because this is just the raw distance that it covers. And oh yeah, I guess. Because this is the 4 point, yeah, so that is the same mistake. That 4.7 is the distance compared to the sorry, do I have to take that into consideration somehow? Probably. Because that's what the case would be if we have the 60.
distance. Maybe that's the time that it would happen if there was no, if the river's velocity was 0. So if the river's velocity is not 0, it actually should affect the distance along the horizontal, not the vertical. So is there some way that I can incorporate that in here? And if so, how? That's a distance. So I've got a, yeah, maybe it's that, maybe an intuition, like,
Professor, I think for your distance formula, the radical,
yeah,
I believe rather than just doing 60 squared, you do 60 plus 1 t
yeah,
squared.
yeah, I agree with you, because it's effectively, from this point of view, it's like I got to travel a farther distance along the x direction. Because yeah, you're right. That's it. Because it's like if I'm pointed here, and I definitely have to angle my thing at a larger angle than what the path is. So it's like I'm actually coming down here someplace. So that distance right there is actually Vy naught time, which is V naught sine theta times t. So I've got to make up this distance right here, kind of in a sense. It's V naught, I guess, it's the y component, so cosine theta naught times t, or really Vy naught times t. And so the way that that extra distance, you said 60 plus what did you say? 60 plus
60 plus 1t, and then
yeah,
I think you could set
1t.
the entire radical to 4.7t.
Yeah, 60 plus 1t, you're right, because this is a distance, so it's got to be distance that I add. So 60 plus, oh, it's not the velocity of the boat, it's the velocity of the river. That's the extra distance I have to travel, which is the 1 Vr times t. You're right. So let's do that. I can't do that again. So 60 plus 1 times t quantity squared plus 240 squared. Okay. And my logic was that that distance yeah, because logically it's this distance, that's actually this distance that I'm traveling, which is V naught times t. So that distance d, you said set it equal to V naught times t, which is force. That's what you said, right? Equate those two.
Yeah, yeah. So
Yeah.
4.7 times t, and then set it equal to the whole radical.
Right. Because that would be this like effective distance that I'm traveling. So I agree. Yeah,
Yeah,
like
that's how I solved for t, and then I got the correct answer.
yeah, so here you have to, it's going to end up being a quadratic, I guess, and you solve it, or is it not? So you set them
Yeah,
V
it's a
naught
quadratic.
equals, yeah. So yeah, whatever that is. So so I guess when you square it, you're gonna have V naught squared times t squared equals quantity 60 plus t 150 squared plus 240 squared. So you solve that, and so that's the thing that you did and solved, and you got you got two solutions from that, yeah.
Yeah, but I chose the positive one.
Okay. What were the values?
The positive one was 56.8. I didn't write the negative one because I figured I wouldn't need it.
Okay. Okay. And
And then
so
the way they're solving for the angle was they used that time and they've used it in tan inverse. So they did the tan inverse of 60 plus 1 times that time and then over 240.
I think that's this equation here, right?
Yeah, yeah.
Because you said tan inverse or cosine. They said because this is Vx V naught. So that's V naught cosine of theta naught minus 1. So like what I was going to say is that, once you have that time, then you could put it stick it back, unless I have those equations wrong, but stick it back either into that guy or that guy. But what you need a tangent for that? Well, sorry, sine.
I guess that's how they solved it, but I didn't try using the other equations. I just figured I'd do tan inverse of like the vertical vector over the horizontal vector.
Maybe that's a different equation they're getting from here. This distance here is, this distance is VR times T. So yeah, that angle right there is going to be the tangent is opposite over adjacent. So the tangent of that angle is going to be equal to the opposite side, which is 60 plus VR times T divided by 240. Is that what you're saying that they used?
Yeah.
Wow. That's actually a pretty good problem. So you got me stumped. Wow. Okay. Yeah, I agree. Inverse tangent -1 of that thing. That's it's not a trivial problem. Plus VR times T. Tangent of theta is inverse tangent. So that's not any of the equations that I had. 60 plus VR times T over 240. And now that we have this time, that's going to work. Ooh. Well, I apologize. I couldn't get it become so easy for me. But yeah, I do agree with what they're doing there. And basically, there were three equations. And so the way my philosophy, the way I work, the three unknowns are Vy naught, Vx naught, and time. And well, actually, it's not true. There's actually more than I guess that's where I made a mistake. There's actually 4 unknowns. There's time. We don't know the time it takes to get across.
We don't know those individual velocities, but kind of like, even though there's only one angle, it's kind of inside this tangent, but the tangent is split into a cosine and a sine. So it's kind of like, I guess if you put them together, because tangent theta is an unknown. Time is an unknown. And I guess the individual velocities are unknowns. So you're going to have more than, basically from the physics, and that, I guess the physics here only gives two equations. And sure, you get a third equation from this geometry, but it kind of introduces two more unknowns, cosine and sine. So when you combine that, I think that takes care of that, but still you don't know time. So I think that what happens is you need another equation, and you're kind of getting that from this thing right here, which is, I didn't think about that. That's a geometric equation, but it's kind of like an equation in math space or something. It's not actually what happens, but it's something that you can use, right? The physical thing that actually happens is this. But this is something that is kind of happening somewhat in theoretical math space. And so you can use it as a, to get equations. And we basically get, yes, two. You can get an equation for the Pythagorean theorem with that distance. And then you can have an equation of just that hypotenuse, which is a physics equation, just applied to the time going across that thing. So yeah, that's something I didn't think about.
Yeah, a lot of the times when I solve these problems, I overcomplicate it, and I don't really see like smaller things like that. And I try, especially with this problem, I kept getting a lot of unknowns, and I didn't know where to go with it. But
well, that's not a
yeah.
bad thing, because I did the same thing and I ran out, and then we kind of did it together. But you remember how I told you that when you come up to when you start to confront problems that are difficult, and this is one. This is, I would say this is an advanced intermediate problem, I would say. What happens is, that's how you know you've missed something, when you keep getting more unknowns than you have. And that's what you just said, right? And I kind of came up to this same thing as well. I said, I don't know how to solve that. I'm missing something. And it's not physics. It's basically, kind of, but it's more a geometrical perception. It's more kind of becomes a mathematical thing. It's like, because I'm teaching concepts, right? There's definitely no physics concepts that we're missing. Kind of, maybe you could say you missed it, going along this line, but the whole idea of that line I wasn't thinking of, and that's not really a physics thing. That's more geometry of, I guess you could say, but you know what I mean? Like it's not something that's actually happening, but it's something that can be described within the mathematical space. So I kind of put that more in terms of geometry than anything else. And so once you see that though, then you know what I mean? So, but that's kind of good, because I was pretty confident that whatever I had done wasn't necessarily wrong, but I just didn't figure out what to do next. And so that's when, I think I said something on the first couple of days, that your creative sensibility, it kind of frees up the possibility of your creative sensibility. Because if you don't have a technique, you can't even get to that point. You think, your confidence is off, you're going around in circles with stuff that, you haven't even got to the point of there's something new here that I'm missing. How can I shift my perspective? And what I told you is, either you go back and you've missed some explicit, implicit information, or you've missed some concepts, and that may be and so to see that, maybe you have to shift your perspective in some way in order to come up with these creative perspectives that you're missing. So this is exactly what I was trying to describe there, because that's what we needed to do in order to solve this problem. But you still kind of maximize your potential in that we did solve it and we definitely understand it.
Yeah.
And we kind of, so now we've kind of extended our understanding, and our technique allowed us to do. So now I'm going to incorporate that back. It becomes part of my basis of knowledge now. So the next time I do a problem, it's not hit or miss, right? The next time I do a problem, since I'm going to go into it with kind of an expanded awareness of something that was not part of my expanded awareness prior to doing this problem. The thing that maximizes that happening is the technique.
Mm-hmm.
You see what I follow what I'm saying?
Yeah, for sure. I mean, the way I think about it is the more times I get it wrong, the closer I am to getting it right.
I mean,
So-
hey, that's great. Scientists have used that philosophy in the past, and the poster boy for that everybody knows the poster boy for that kind of approach is Thomas Edison, right?
Yeah.
He did everything. I don't know how many. You can Google it. How many times he just, and he knew it. He wasn't like, I don't have to be a genius. I just have to do all the wrong things, and then at some point, there's not going to be anything left. So with the light bulb, that's what he did. And there's a certain number that he counted how many times he created a light bulb that didn't work, and then it just left the thing that we ultimately used, right? So a win is a win, right?
Exactly.
So yeah.
Well,
Well,
I appreciate you staying after class and helping me with this. I know it took a little bit of time, but thank you so much for the help.
Yeah, no worries. Yeah, it's really interesting to me, and I'd never done a problem like this before, clearly. And so now I'm gonna kind of recopy it and go over it again and kind of put it in my because it got when something like this happens, you want to kind of reinforce it, right? So I'm gonna kind of do it again, write it out, as a part, like if I were, new notes in my Rolodex of information. Just kind of go back and you want to make it your own, right? So I need to explain it in the context, kind of how I was doing. I need to go back and check some things as well and kind of figure out why I didn't see it quicker or whatever, and put that in. Yeah. So cool. Yeah, this was awesome. It's really interesting when you kind of feel yourself learn something new for the first time. It doesn't happen that often anymore, but when it does happen, it still feels kind of good, I mean, that's the upside of getting something wrong, basically what you just said, but maybe it's saying it a slightly different way. But it's really interesting. I'm also going to look at that negative solution, because you know how I like to do that. Like, what does that negative solution mean?
Yeah.
What is that supposed to? Yeah. All right. Well, cool. Well, so this one, I guess you got half credit, so that's pretty good. But I think that one's going to stand in terms of the grade. Fair enough?
Okay. Yeah, fair. Thank you, Professor.
All right. Thank you so much, Emily. All right. Keep
Have a
working
good day.
hard. All right.
Thank you.
Too. Bye-bye.